Welcome to the Sleepy Professor. Tonight, as you settle into the gentle embrace of evening and let the weight of the day dissolve like mist at dawn, we're embarking on a journey into one of existence's most profound mysteries. We're going to drift through the cosmos, exploring the invisible substance that binds everything together, a cosmic glue so fundamental that without it, the universe as we know it simply wouldn't exist. It's called dark matter, and though it makes up most of the cosmos, filling every corner of space like an invisible ocean, we've never actually seen it, not even once. So, if you're ready, dim the lights around you, take a slow deep breath, feel your shoulders drop, and let's drift gently into the dark matter of space, where the greatest secrets hide in plain sight. Before we begin our cosmic voyage, I'd love to know, where in the world are you listening from tonight? It's always fascinating to see how far curiosity travels before bedtime, from bustling cities to quiet countryside, from one hemisphere to another, all of us united by wonder. If you're new here, welcome to this sleepy little corner of the universe. Please consider giving the video a like and subscribing for more calm, curious explorations of science and the cosmos. To those already part of this community, thank you sincerely. You make these journeys meaningful. Don't forget to tap the notification bell so you'll never miss our next quiet adventure through the stars. I hope this video isn't so interesting that it keeps you awake, but if it does, at least you'll fall asleep a little wiser, with your mind full of the universe's most elegant mysteries. The invisible architecture. So, what exactly is holding galaxies together when there's not enough visible matter to do the job? What keeps the cosmic machinery running when all the gears we can see aren't enough? Dark matter. The phrase itself sounds like something plucked from the pages of science fiction, mysterious, invisible, perhaps even ominous. You might picture something sinister lurking between the stars, but in truth, it's the quietest and most patient part of the universe. It doesn't announce itself. It doesn't demand attention. It doesn't glow, spark, or collide. And yet its invisible weight sculpts the cosmos into the magnificent shape we see tonight. For nearly a century, astronomers have watched galaxies behave in ways that shouldn't be possible. Stars spin faster than they should, yet somehow don't fly apart into the cosmic void. Entire clusters of galaxies drift through space, as though guided by unseen hands, holding together when everything we know about gravity says they should scatter like autumn leaves in a storm. Each observation, each careful measurement, whispered the same persistent truth. There's more out there than light can tell us. Far more. Tonight, in this calm exploration, we'll drift from those first strange observations that puzzled scientists to the vast cosmic web of invisible filaments stretching between galaxies like a spider's silk, catching the morning dew. We'll follow the evidence written in the bending of starlight as it crosses the universe and in the ancient afterglow of the Big Bang itself. Along the way, we'll meet the tiny hypothetical particles that might make up this dark mass and explore the ingenious experiments hidden deep underground that are still listening, patiently, for their whisper. No dense equations tonight, no heavy jargon that weighs down the mind, just the slow, steady rhythm of a mystery that has shaped everything we know, from the smallest atom to the largest galaxy. As you relax deeper into your pillow and listen, imagine the universe as a great cosmic tapestry, woven mostly from threads you cannot see. The stars, those brilliant points of light we admire, are only the embroidery, beautiful surface details stitched onto something far grander. The true fabric lies beneath, silent and unseen, the dark matter of space, holding everything in its invisible embrace. The first whisper, Fritz Zwicky's discovery. In the quiet decades between the two world wars, when telescopes were still guided by patient human hands and astronomical photography required hours of stillness, measured not in seconds, but in the slow turning of Earth itself, a Swiss astronomer named Fritz Zwicky began studying a cluster of galaxies far beyond our own cosmic neighborhood. It was called the Coma Cluster, a vast congregation of more than 1,000 galaxies, each one containing billions upon billions of stars, all drifting together through the dark sea of intergalactic space like a school of luminous fish moving through an infinite ocean. Zwicky was fascinated by its structure. He had that particular kind of curiosity that doesn't accept things at face value, the kind that pokes and prods at reality until it reveals its secrets. But as he studied the cluster more closely, measuring and calculating with the precision that defines good science, something profound didn't add up. The numbers refused to behave. He measured the speeds at which the galaxies were moving, how fast they raced around within the cluster, and what he found was deeply puzzling. They were moving far too fast. According to Newton's venerable law of gravity, which had explained planetary motion for centuries, the visible matter in those galaxies simply wasn't enough to keep the cluster together. The mathematics were clear and unforgiving. Those galaxies should have flown apart long ago, scattered across the universe like sparks from a firework, each one racing off into the endless dark. But they hadn't. They were still there, still bound, still orbiting within the cluster's gravitational embrace, as if held by invisible chains. The numbers told a strange and unsettling story. The Coma Cluster appeared to weigh hundreds of times more than what its visible stars and glowing gas could possibly account for. It was as if you stepped on a bathroom scale expecting to weigh 150 pounds, but the needle swung to 15,000. Zwicky, with his famously sharp tongue and impatient brilliance, he was not known for suffering fools gladly, called this missing ingredient dunkel materie, dark matter. It wasn't meant to be poetic or dramatic. He simply needed a name for whatever invisible something was holding everything together, keeping the cosmic dance from dissolving into chaos. His calculations were based on what's called the virial theorem, a straightforward principle in astrophysics that connects how fast things move within a system to how much mass that system must contain. In simple terms, if galaxies move faster than expected, there must be extra gravity keeping them from flying away into the void. Gravity, after all, follows one inexorable rule: the more mass you have, the stronger your pull. There are no exceptions, no loopholes. Zwicky's observations implied that there was a vast amount of unseen mass providing the gravitational glue. It was there, it had to be there, or the Coma Cluster would have dissolved eons ago. At first, few people paid attention. Part of the problem was Zwicky himself. He had a reputation for being, let's say diplomatically, somewhat difficult to work with. He once famously described some of his colleagues as spherical bastards, meaning they were bastards no matter which way you looked at them. Brilliant, absolutely. Diplomatic, not in the slightest. But even if his personality grated on others, and made them reluctant to embrace his ideas, his mathematics did not lie. The numbers were stubborn, persistent things. The Coma Cluster really did move as if it were full of hidden weight, as if some invisible hand were holding it together. The idea of missing mass seemed too strange, too outlandish for many astronomers at the time. The universe was still thought of as a place made primarily of visible things: stars burning bright, clouds of luminous gas, dust lanes, silhouetted against glowing nebulae, and the occasional planet. The notion that most of its substance might be completely invisible was almost unthinkable, like suggesting that most of a painting exists on a canvas you can't see. Perhaps colleagues suggested Zwicky had made an error in his measurements. Telescopes were improving, but they weren't perfect, or maybe the light from distant galaxies was being distorted in ways they didn't yet understand. It was easier, and far more comfortable psychologically, to assume that the problem lay in the data rather than in the fundamental nature of the universe itself. Yet the numbers kept whispering the same persistent story. The galaxies in the Coma Cluster were moving too quickly for their visible light to explain. Even if you added up every visible star, every glowing cloud of gas, and every faint wisp of starlight, it still wasn't enough. Not even close. Something else, something fundamentally unseen, had to be providing most of the cluster's mass. To picture it more clearly, imagine floating in the void of space, looking down upon the Coma cluster from some impossible vantage point. Thousands of galaxies gleam like lanterns set adrift on a dark sea, each one a city of stars containing more suns than you could count in a lifetime. Between them lies nothing but blackness, an absence so complete it feels like looking into the void itself. But that blackness isn't truly empty. It's heavy, with something invisible, an unseen web that binds each lantern firmly in place. If you could somehow reach in and strip away that hidden mass like pulling threads from a tapestry, the galaxies would scatter instantly like sparks from a dying fire, leaving only cold emptiness behind. Zicky's discovery planted a seed of doubt in the neat, luminous picture of the cosmos that had satisfied astronomers for generations. For the first time, scientists were forced to seriously consider that what they could see, the glittering stars and glowing nebulae that filled their photographic plates, might be just the thin, bright surface of something far greater and more mysterious. He couldn't know it then, standing at his telescope in the quiet Swiss night, but his lonely calculations were the first cracks appearing in the universe's bright facade. Behind the light, a shadowed architecture was waiting patiently to be revealed. It would take decades for others to notice those cracks widening, and nearly a century later, humanity would still be trying to understand what lies behind them. What Zichy had stumbled upon wasn't a trick of measurement or a temporary gap in the data that would be filled with better instruments. It was a truth so large, so fundamental, that it would eventually reshape cosmology itself. The visible universe, it turned out, was not the whole story, not even close. The luminous galaxies that filled the night sky were only the decorations on a far grander, darker structure. It's an oddly comforting thought when you let it sink in. Even in the vast darkness of space, there is structure, there is balance, and there is hidden order. The Coma cluster didn't need more stars or brighter light to stay together. It needed the quiet weight of the unseen, the gravity of something that asks for no attention, offers no glow, produces no fanfare, but holds everything in its invisible place nonetheless. Fritz Zwicky didn't have the tools or technology to see what that something was. He had only the courage to point out that it must exist, and the stubbornness to insist on it even when others dismissed him. His data didn't reveal a new kind of star or planet. It revealed a new kind of ignorance, a profound reminder that the universe still had secrets it wasn't ready to share. And as the decades passed, astronomers would begin to notice the same strange imbalance in other galaxies too. The whisper that began in the Coma cluster would grow louder, echoing across the cosmos in observation after observation, until scientists could no longer ignore it or explain it away. What Zwicky saw in that cluster of drifting lanterns was not an anomaly, not a fluke, not a mistake. It was the first hint of a hidden order shaping everything we see, a whisper that would become a pattern that would become undeniable truth. The revolution of Vera Rubin. By the middle of the 20th century, astronomy was undergoing a quiet revolution. New telescopes were turning their increasingly precise gaze outward, and astronomers were beginning to map not just where galaxies were, but how they moved, the intimate choreography of stars within those island universes. Among those astronomers was Vera Rubin, a calm, meticulous scientist who loved the night sky and the quiet rhythm of data as much as she loved the galaxies themselves. She wasn't chasing fame or trying to prove grand theories. She simply wanted to understand how galaxies moved, to see the patterns hidden in their rotation, to read the story written in starlight. Rubin's work focused on spiral galaxies, those graceful, swirling disks of stars that look almost peaceful when photographed through telescopes, like cosmic whirlpools frozen in time. But behind their serene beauty lay a puzzle that would fundamentally change how we understand the universe. The physics seemed straightforward. When a galaxy spins, its inner regions, the stars huddled closer to the center, should move faster than those on the outer edges. That's how gravity works on large scales, and it's exactly what we see in our own solar system. The farther you are from the concentrated mass in the middle, the weaker the gravitational pull becomes, and the slower your orbit should be. It's an elegant, predictable pattern. Mercury, snuggled close to the Sun, whips around its parent star in a tight, rapid orbit that takes only 88 days. Neptune, drifting far out on the solar system's cold edge, takes over 160 years to complete a single lazy lap. The rule is mathematically beautiful and comfortingly predictable. The farther you are from the center, the slower you should travel. But when Rubin and her collaborator Kent Ford began carefully measuring how fast stars actually moved around their galaxies, using sophisticated spectrographs attached to powerful telescopes, the data refused to cooperate. It refused to follow the rules. They used the Doppler shift, that subtle change in light's wavelength as objects move toward or away from us, to trace the orbital speed of stars at different distances from the galactic center. It's the same principle that makes an ambulance siren change pitch as it rushes past you on the street. Light from stars moving toward us shifts slightly bluer. Light from stars moving away shifts redder. By measuring these tiny shifts with exquisite precision, they could calculate exactly how fast each star was traveling. The results were stunningly consistent across galaxy after galaxy, and completely, utterly unexpected. Instead of slowing down as they got farther from the center, the stars on the outskirts of galaxies were moving just as fast as the ones near the middle. The rotation curves, graphs plotting orbital speed versus distance from the center, didn't fall off in that gentle, expected hill. Instead, they flattened out dramatically, stretching horizontally across the chart like a plateau, as if the outer stars had collectively decided to ignore Newton's laws entirely. Galaxies, it seemed, were remarkably good at ignoring instructions to slow down. Rubin described her findings with careful scientific restraint, as good scientists do. But behind that measured language and those precise data points was something absolutely astonishing, something that should have been impossible. According to the well-established laws of gravity that had explained celestial mechanics for centuries, these galaxies should have flown apart long ago. The visible mass, all the shining stars, glowing dust lanes and brilliant clouds of ionized gas, simply wasn't enough to keep the outer stars gravitationally bound to the galactic center. Yet the galaxies held together beautifully, rotating in steady, graceful defiance of expectation. They spun like solid wheels rather than loose collections of independent stars. Something unseen had to be adding tremendous amounts of extra gravity, not just a little bit, but several times more gravitational pull than all the visible matter combined. Whatever this invisible component was, it wasn't emitting any light across any wavelength. It wasn't colliding with normal matter like gas clouds do, and it wasn't hiding behind veils of dust that telescopes could eventually pierce. It was simply there, invisible but absolutely undeniable, forming a vast spherical halo around each galaxy, reaching far beyond where the last stars twinkled at the luminous edge. To picture it more vividly, imagine a record player turning slowly in a darkened room. You can see the glowing dots near the center, spinning swiftly, but even the faint ones near the outer rim circle with surprising, inexplicable speed, refusing to lag behind as they should. The music, in this case, the gravitational symphony, plays evenly from center to rim. The galaxy is the record, and the invisible dark matter halo is the steady hand keeping the rhythm constant, preventing the outer notes from fading away. Rubin's data wasn't just a curious anomaly from one unusual galaxy. As she methodically studied more and more of them, from tiny dwarf galaxies barely visible in telescopes to enormous spirals spanning hundreds of thousands of light years, the same pattern emerged again and again and again: flat rotation curves, fast outer stars, hidden mass. What began as a single puzzling observation transformed into an undeniable rule of nature, a fundamental property of how galaxies actually work. Her results were met with skepticism at first, as most revolutionary findings inevitably are. The scientific community tends toward conservatism, preferring to modify observations rather than overturn established understanding. The idea that galaxies might be surrounded by enormous cocoons of completely unseen matter felt outlandish, even absurd. Perhaps, critics suggested, there was a subtle problem with the data. Maybe the instruments had systematic errors. Possibly the analysis methods were flawed, or the sample size was too small to draw such dramatic conclusions. Rubin, however, was thorough to the point of absolute perfection. She was meticulous in ways that would put Swiss watchmakers to shame. She repeated her measurements with different instruments. She refined her techniques. She expanded her sample size to include dozens, then hundreds of galaxies. She checked and rechecked every calculation until the evidence became utterly unassailable, building a case so solid that even the most hardened skeptics had to acknowledge its validity. The galaxies weren't misbehaving. They were revealing the universe's true architecture, showing us that reality was stranger and more magnificent than anyone had imagined. What made Rubin's work so remarkable wasn't just the precision of her science or the revolutionary nature of her discovery. It was also the quiet grace with which she carried it out. She didn't frame her discovery as some cosmic upheaval meant to shake the foundations of physics. She didn't trumpet it as proof of her genius or demand recognition. She treated it simply as a natural part of learning, another layer of truth waiting patiently for humanity to notice, like a gift that had always been there but required the right eyes to see it. She once said with characteristic modesty, "We are still groping for understanding." It wasn't a confession of confusion or failure, but an expression of profound wonder, an acknowledgement that the universe is endlessly surprising, and that our journey of discovery is never truly complete. The implications of her work were staggering. If every galaxy needed an invisible halo of dark matter several times more massive than all its stars just to hold itself together, then dark matter must be everywhere. It must be woven through the entire cosmos like an invisible fabric, anchoring every cluster, every filament of the cosmic web, every structure we observe. It wasn't a rare cosmic oddity confined to a few strange galaxies. It was the dominant form of matter in the universe, making up the vast majority of gravitating mass. The bright stars and glowing nebulae we admire with telescopes and photograph for textbooks are just the decorative frosting on a vast invisible cake. The substance beneath is dark, silent, and absolutely essential. Vera Rubin didn't claim to know what dark matter actually was, what particles composed it, where it came from, why it behaved so differently from normal matter. She knew only, with scientific certainty, that it must be there. That certainty, backed by mountains of careful observations, reshaped modern astrophysics in ways that are still unfolding today. The universe was suddenly heavier, stranger, and somehow more beautiful than anyone had imagined. For every twinkling point of starlight you see in the night sky, there's an invisible ocean of dark matter, making sure it stays exactly where it should be, preventing it from drifting off into the cosmic void. Her discovery also highlighted something profound about the nature of science itself. Sometimes the universe doesn't shout its secrets from the rooftops. Sometimes it doesn't announce revolutionary truths with dramatic explosions or obvious signs. Instead, it whispers them through subtle patterns that refuse to fade away, through lines on graphs that stubbornly stay flat when they should slope downward, through numbers that quietly insist on telling a different story than we expected. A flat line on a graph can be as earth-shaking as a supernova explosion, as revolutionary as any dramatic cosmic event, but only if we have the patience to listen, the wisdom to trust the data over our preconceptions, and the courage to accept what the universe is trying to tell us. Rubin's galaxies continued to spin through the cosmos, calm, elegant, and slightly rebellious, as if reminding us with every rotation that light is not the only way to measure reality. That visibility is not the same as existence. Behind every star, sustaining its orbit, is the quiet pull of the invisible, and behind every great discovery is someone who noticed when the numbers didn't behave, someone who paid attention when something seemed slightly off, someone who refused to look away when the universe whispered a secret. When Vera Rubin passed away in December of 2016, the scientific world mourned not just the loss of a brilliant mind or a pioneering researcher, but the gentle curiosity and humble persistence she embodied throughout her life. Her work didn't just confirm the existence of dark matter or prove Zicke had been right decades earlier. It transformed dark matter from a vague, easily dismissed idea into an absolute cornerstone of modern cosmology, as fundamental to our understanding of the universe as stars or gravity themselves. She showed us that even in the grand, impersonal scale of the universe, where galaxies spin for billions of years and distances are measured in numbers our minds can barely comprehend, progress often begins with the simple act of noticing something small, a graph that refuses to tilt downward, a star that spins too fast, a pattern that doesn't match expectations. In the end, her galaxies kept their rhythm unchanged by her death or our understanding. They turned unhurried and unbothered, guided by those same invisible hands, following the paths carved by dark matter, halos billions of years ago. Each one stands as a perpetual reminder that the universe's greatest forces, the ones that truly shape reality, are not always the ones we can see with our eyes or photograph with our instruments. The light shows us beauty and paints pictures across the cosmos, but the dark reveals truth, the fundamental architecture underlying everything. And in that delicate balance between brightness and shadow, between the seen and the unseen, lies the quiet heart of the cosmos, spinning forever through the endless night. Gravity's honest pen. Gravity is a bit like an incorrigible gossip in the cosmic neighborhood. It cannot keep a secret, no matter how hard it tries. No matter how invisible something might be, no matter how thoroughly it hides from every telescope and detector we've ever built, if it has mass, gravity will inevitably tell on it. Gravity bends light, tugs on stars, distorts the shapes of galaxies, and leaves unmistakable fingerprints wherever it acts. You can hide from every electromagnetic telescope ever constructed. You can evade every particle detector. You can slip through every filter and dodge every observation, but you absolutely cannot hide from gravity's honest testimony. Every object with mass curves the fabric of space-time around it. Einstein's general theory of relativity, one of the most beautiful and radical ideas in the history of physics, showed us that gravity isn't really a force pulling things from afar like invisible strings or magical attraction. It's something far more elegant. It's the actual shape of space-time itself. Think of it this way: a star, a planet, even you sitting or lying down at this very moment, are all pressing gently into the cosmic fabric, warping it ever so slightly like a bowling ball placed on a stretched rubber sheet. The heavier something is, the deeper its indentation becomes, the more dramatically it curves the space around it. When light travels through this warped terrain, it doesn't travel in the straight lines we learned about in school. It bends and twists along those gravitational curves, following the contours of space-time itself, not because it wants to, not because anything is physically pulling on it, but simply because the path itself, the very geometry of space, has changed. This is precisely why, Even though dark matter doesn't shine or reflect a single photon of light, we can still see where it hides. We can map its presence with remarkable precision. The light from distant galaxies gets stretched, bent, split, or even perfectly duplicated as it passes through regions filled with invisible mass. Astronomers can trace those distortions and reconstruct the unseen landscape behind them with the precision of archaeologists reconstructing ancient ruins from scattered fragments. It's like watching ripples spreading across a pond and knowing with certainty that something large is moving beneath the opaque surface. Even though the water itself remains murky and impenetrable to your eyes, the ripples tell you exactly where the invisible swimmer is and how massive it must be. When stars move too quickly within their galaxies, when light bends in unexpected and beautiful ways, when galaxies cling together with gravitational strength that far exceeds what their visible mass should provide, gravity is whispering the same fundamental thing over and over. There's more here than meets the eye, much more. To make sense of this profound idea, picture the universe as a vast river system stretching across a continent. The glowing stars and brilliant galaxies are the shimmering reflections you see dancing on the surface. Beautiful, captivating, but ultimately superficial. They're what catches your eye when you first look. Beneath that glossy, calm surface, however, flow powerful unseen currents, the gravitational influence of dark matter. You cannot dip your hand into the water and feel those currents directly. You cannot bottle them or examine them under a microscope. But everything you see on the surface moves because of them, shaped by their invisible flow. For all its tremendous influence throughout the cosmos, dark matter is extraordinarily well behaved. It doesn't crash into itself in violent collisions. It doesn't spark or flare with energy. It doesn't absorb light or emit it. It simply passes through space like a ghost passing through walls. Physicists call this property non-collisional, which is a technical way of saying that while ordinary matter, the stuff that makes up you, me, planets and stars, constantly bumps and interacts through electromagnetic forces, exchanging energy and momentum, dark matter glides serenely through itself and through us as though we weren't even here. It experiences gravity, and as far as we can tell, little else matters to it. If dark matter did interact strongly with itself or with light, the universe would look entirely different from what we observe. Galaxies might glow with unexpected radiation across strange wavelengths. Their shapes might distort and clump in bizarre ways that our telescopes would easily detect. But they don't. The night sky remains as pristine and serene as ever, its darkness perfect and undisturbed, which tells us with increasing certainty that dark matter remains fundamentally aloof from the electromagnetic chaos of ordinary matter. This strange detachment, this cosmic introversion, also explains why dark matter formed the backbone of the cosmos in the first place. In the early universe, when everything was unimaginably hot and crowded, more dense than anything we can recreate in laboratories, normal matter couldn't settle down into structures. Photons, the particles of light, kept scattering violently off charged particles, stirring everything constantly like an aggressive chef mixing cosmic soup. Nothing could clump together. Nothing could rest. Dark matter, however, stayed cool and emotionally indifferent to all this electromagnetic chaos. Unaffected by the furious light that kept ordinary matter stirred up, it began gathering quietly under its own gravity from the very beginning, forming the first clumps and concentrations, the gravitational seeds of all future galaxies, the foundation upon which everything visible would eventually build. When the universe finally cooled enough for ordinary matter to calm down and stop being buffeted by radiation, that matter fell naturally into the dark matter wells that had already formed, like sand settling into the grooves of a riverbed, following paths that had been carved out eons before. In this very real sense, dark matter acted like a silent architect working in the dark before anyone else arrived. It didn't build galaxies by hand, didn't place each star with intention, but it shaped the fundamental terrain on which they would inevitably rise. Without dark matter's early scaffolding, the universe might still be nothing but a thin, uniform fog of gas and radiation, bright perhaps, but utterly empty of structure, devoid of galaxies, stars, planets, and life. The supreme irony, of course, is that gravity itself is actually the weakest of all the fundamental forces by far. Within an atom, electromagnetic forces are vastly stronger. The strong nuclear force that holds atomic nuclei together is incomparably more powerful at its scale. Yet over cosmic distances, over millions and billions of light years, gravity becomes overwhelmingly dominant simply because it never stops adding up, never cancels out, never quits. It's the most patient sculptor imaginable, the one that never tires, never takes a break. Over billions of years, its gentle but absolutely relentless persistence rearranges stars, clusters, and entire galaxies into the magnificent patterns we can observe from across time and space. And every one of those patterns, every graceful spiral and elegant structure, carries the subtle trace of the dark matter that guides it. Sometimes, the universe reveals these traces in absolutely dramatic fashion. When two massive clusters of galaxies collide, events so violent they involve hundreds or thousands of galaxies crashing together, something remarkable happens. Their visible gas clouds, each one millions of degrees hot, crash together and slow down dramatically, heating up into brilliant bright knots that glow intensely in X-ray wavelengths. But the dark matter halos, they pass straight through one another like ghosts walking through walls, utterly unaffected by the collision. The galaxies themselves and their superheated gas pause for a cosmic moment, releasing tremendous energy. But the dark matter continues its ancient dance completely indifferent to the commotion, following only gravity's patient pull. The result is a spectacular cosmic separation of light and gravity, visible and invisible, seen and unseen, one of the clearest possible signs that dark matter is genuinely real and that it plays by its own quiet, separate rules that have nothing to do with electromagnetic forces. For astronomers studying these cosmic collisions, these moments are like suddenly catching a clear glimpse of those invisible currents beneath the glassy river we discussed earlier. The galaxies drift and swirl in their visible glory. The light bends and stretches according to Einstein's equations, but the pattern always points back to the same hidden hand guiding it all, the same invisible presence that's been there all along. Gravity has written dark matter's signature across every corner of the sky in letters vast and unmistakable, and all we have to do is learn to read that elegant script. It's remarkable when you pause to think about it. Everything we know about dark matter, every single fact, every measurement, every conclusion, comes not from seeing it directly, not from capturing even one particle or detecting even one photon, but from watching how it moves and influences the things around it. It's like trying to learn the exact shape of an animal you can never see by studying only how it disturbs the grass as it moves, or understanding a dancer entirely by watching their shadow on the wall. Over decades of careful observation, astronomers have pieced together a surprisingly detailed portrait from these gravitational hints alone. They've determined that dark matter forms massive halos around galaxies, that it connects galaxies with invisible bridges spanning millions of light years, that it holds the universe's entire structure in place like the skeleton holds a body upright. This invisible mass doesn't break the laws of physics or require us to throw out centuries of careful science. Instead, it completes them, filling in gaps we didn't even know existed. Without dark matter, gravity's elegant equations would predict chaos, stars drifting apart, clusters dissolving, galaxies never forming in the first place. With dark matter included, everything gains beautiful coherence, as though an unseen hand steadied the spinning record of the cosmos at the moment of creation. So while light may be the vibrant painter that colours the universe in brilliant hues, gravity is the honest pen that sketches its underlying outlines. Every curve in space, every orbit traced by celestial bodies, every gleaming spiral galaxy we admire through our telescopes is drawn upon a framework fundamentally shaped by the unseen. If you trace those gravitational lines far enough, following them across the cosmos like a detective following clues, you find that they connect into a vast interlocking structure spanning the observable universe, delicate yet immense, fragile-looking yet impossibly strong. Gravity, patient and ever honest, unable to lie or dissemble, has revealed the true shape of what light alone could never show us. The invisible doesn't hide from our understanding out of malice or deception. It simply doesn't need to shine to be profoundly, fundamentally real. It moves the galaxies with invisible hands. It bends the light into beautiful arcs. It writes the basic architecture of everything that exists in the cosmos. If gravity is indeed the universe's honest pen, then it has drawn for us a magnificent web, an intricate, invisible masterpiece stretching through the dark, binding all things together in perpetual silence. The cosmic web microarchitecture of the universe. When astronomers began mapping the universe in 3 dimensions using powerful telescopes and sophisticated techniques, they expected to find galaxies scattered, more or less evenly through space, perhaps clustering here and there in denser regions, but generally spread out like grains of sand scattered across a vast beach, random with no particular pattern. Instead, what emerged from their data was something absolutely astonishing, something nobody had quite anticipated. They discovered a grand, interconnected structure stretching across billions of light years, spanning distances so vast that light takes longer to cross them than complex life has existed on Earth. It looked less like random scattering and infinitely more like a vast 3-dimensional network, delicate yet complex, woven from invisible cosmic threads. This immense pattern became known as the cosmic web, and it is, quite literally, the skeleton of the universe, the fundamental architecture upon which everything else hangs. The glowing galaxies and brilliant clusters of galaxies trace its filaments like luminous beads strung on invisible strings, like city lights following highways you cannot see from space. Between these glowing filaments lie immense voids, vast regions of almost perfect emptiness, where hardly a single galaxy resides, cosmic deserts so empty that if you placed our entire Milky Way galaxy in the center of one, you might never find another galaxy within your visible horizon. To see this web mapped out is to glimpse the quiet architecture of creation itself, the dark scaffolding upon which all the light of the cosmos hangs like ornaments on an invisible Christmas tree. At first glance, it's genuinely difficult to imagine how such an intricate, organized structure could have formed from the near-uniform soup of the early universe. After all, shortly after the Big Bang, the cosmos was almost perfectly smooth, a hot, dense fog of particles and radiation, with only the tiniest imaginable ripples in density, subtle variations of literally 1 part in 100,000. Those faint ripples were almost nothing, barely there at all. Yet those impossibly faint ripples were like precious seeds containing everything to come, the blueprint for all future structure. Where there was just slightly more matter than average, even by the tiniest fraction, gravity began its patient work, gathering material slowly but inexorably, drawing it into progressively denser knots over millions and then billions of years. Over cosmic timescales that beggar human imagination, those microscopic density differences grew into the magnificent filaments and enormous clusters we see today spread across the universe. Dark matter was the quiet, tireless builder behind it all, the construction crew working night and day in complete darkness. Ordinary matter, the kind that glows and forms stars and planets, was simply too busy interacting with the intense light flooding the early universe. It was hot, restless, and far too easily scattered by radiation to settle down into any structure, like trying to build with water while hurricane winds blow. Dark matter, on the other hand, doesn't care about light at all. Photons pass through it without effect. It simply moves under the influence of gravity alone, elegantly simple in its behavior. It began clumping together long before anything visible could possibly follow, forming invisible channels and wells in space-time itself. Once the dark matter had patiently formed its invisible web over millions of years, ordinary matter finally cooled enough to flow into those preformed channels like water finding riverbeds. It pooled in the deepest gravitational wells and gradually cooled further until, finally, the first stars ignited, tiny sparks of light appearing in the cosmic darkness. The result we see today is an intricate balance of light and shadow that would make any artist weep. Luminous galaxies shine brilliantly along the dense filaments of unseen matter, surrounded on all sides by vast, empty voids stretching for hundreds of millions of light years. These filaments stretch across unimaginable distances, some spanning hundreds of millions of light years from end to end. If you could somehow step outside the universe entirely and look down upon it from some impossible vantage point beyond space and time itself, it might resemble several things at once. The neural network of a vast brain with thoughts flickering along its pathways, or the branching roots of an impossibly large tree spreading through dark soil, or perhaps the three-dimensional foam in a cosmic cappuccino, all glowing faintly against an infinite black canvas. Astronomers often describe the web using words borrowed from biology, geology, or anatomy. Because the patterns feel strangely organic, they speak of filaments, like the fibers in muscle tissue, nodes, like the junctions in a network, clusters, like cells grouping together, and voids, like the empty chambers in bone structure. The filaments are the long, thin strands connecting everything, like cosmic highways along which galaxies travel. The nodes are the intersections where multiple filaments meet, the densest regions in the entire universe where galaxy clusters form, containing thousands of galaxies packed relatively close together. The voids are the dark, empty spaces in between, vast cosmic deserts that make up most of the universe's volume. It's remarkably similar to foam rising in a glass, or the bubbles in rising bread dough, except here the bubbles themselves are empty of galaxies, and the thin walls between them are where all the matter has collected, creating luminous structures. To study this grand cosmic design in detail, scientists rely on massive galaxy surveys, ambitious projects that sweep the night sky systematically to measure the positions and distances of millions upon millions of galaxies. When all that data is plotted carefully in 3 dimensions, the picture that emerges is genuinely breathtaking. Not a random spray of points scattered by chance, but an elegant tapestry of structure, astonishingly organized. Each filament seems to hum with gravity's quiet pull. Every void whispers of cosmic balance. The pattern repeats across scales, from small to incomprehensibly large. But some striking thing about the cosmic web, the observation that really makes scientists confident they understand what's happening, is that its basic shape and structure can be reproduced almost perfectly using computer simulations. These sophisticated models, built on what cosmologists call the lambda CDM framework, lambda cold dark matter, start with remarkably simple physics. The expansion of space according to Einstein's equations, gravity pulling matter together according to Newton and Einstein's laws, and the presence of dark matter that moves slowly. That's the cold part and interacts only weakly with everything else. From those humble, simple ingredients, just a few basic rules and some initial conditions matching the early universe, an entire digital universe blossoms in the computer's memory. In these simulations, dark matter is represented by millions or even billions of individual particles that attract each other gravitationally as the virtual universe expands around them. Over simulated time watched in fast forward by scientists, tiny clumps merge gradually into larger structures. Those larger structures merge into still larger ones, forming long interconnected filaments and dense nodes that look astonishingly, almost eerily similar to what our most powerful telescopes observe in the actual sky. It's one of the great triumphs of modern cosmology, a beautiful vindication of our understanding. With just a few key ingredients, a handful of fundamental principles, and the patient hand of gravity operating over billions of years, the universe naturally weaves itself into a cosmic web. The patterns emerge inevitably, like snowflakes forming from water vapor, complex and beautiful, yet following simple underlying rules. The lambda, in the model, represents dark energy, that mysterious force, even more puzzling than dark matter, that drives the universe's expansion to accelerate rather than slow down. Cold means that dark matter moves relatively slowly compared to the speed of light, allowing it to clump together under gravity instead of zipping around too fast to form any structure. Together, these two invisible components, dark matter providing gravitational scaffolding and dark energy stretching space itself, make up about 95% of everything that exists in the cosmos. Dark matter accounts for roughly 27% of the universe's total mass energy. Stars, planets, gas, and everything else we can actually see, everything made of normal atoms, makes up only the remaining 5%. In other words, the cosmos we know and love, the universe we can see with our eyes and touch with our hands, is just the faintest shimmer outlining a vast unseen design. We're living on the visible surface of something much deeper and stranger. It's a genuinely humbling realization when you let it sink in. The grandest patterns in the universe, the structures that define its very shape, are drawn not by brilliant light, but by the profound absence of it. Every glowing galaxy we admire is just a small lantern hung carefully on the vast framework of the dark. The cosmic web is a masterpiece painted in reverse, its truest, deepest lines defined by what we cannot see, will never see, may never be able to detect directly. There's a quiet elegance to how this structure balances emptiness and fullness, void and substance. The filaments themselves are narrow and dense, packed with galaxies, but the voids between them are absolutely immense, vast beyond easy comprehension. The universe, it turns out, is mostly empty, but not meaninglessly so. Those empty regions, those cosmic voids, allow the dense regions to exist in the first place, just as silence gives essential shape to music, just as the spaces between notes define the melody. Without voids, the web could not breathe. Without darkness, the light could not shine with such brilliance. They define each other, need each other. Astronomers have even discovered that the web's filaments influence how galaxies spin and grow over time. Galaxies tend to align themselves along these invisible threads, their orientations and spin directions subtly shaped by the flow of matter streaming through the vast network. It's as though the entire universe shares a subtle choreography, every galaxy moving to the rhythm of a gravitational symphony that began billions of years ago when the first structures were forming. To imagine this more tangibly, think of the delicate veins in a leaf, or the intricate filigree of frost spreading across a winter window. Each tiny branch, each graceful curve forms naturally, inevitably, following simple physical rules repeated over and over and over again at different scales. Gravity does exactly the same thing on a cosmic scale, patiently turning initial chaos into emergent order with nothing but time and simple mathematics. There's even a kind of unexpected poetry to the voids themselves, those enormous, almost perfectly empty regions between the bright filaments. Some of them are hundreds of millions of light years across, containing fewer galaxies than you can count on both hands. These cosmic deserts are so profoundly empty that if you somehow placed our entire Milky Way galaxy in the exact center of one, you genuinely might never find another galaxy within your observable horizon. The next nearest galaxy could be farther than light could travel in the remaining lifetime of the universe. And yet, they are not barren in any sad or lonely way. They are peaceful. Vast pauses in the cosmic composition, rests between the notes. Their emptiness has dignity and purpose. From the outside, viewed on the largest scales, the web appears calm and eternal, timeless, but it's actually slowly evolving even now. Galaxies continue to fall along the filaments like water flowing downhill, merging and growing more massive. The voids continue to expand, gently pushing the filaments farther apart as the universe itself stretches under dark energy's influence. Over billions of years yet to come, the cosmic web will gradually thin out, its threads elongating and thinning like taffy being pulled, until distant galaxies fade beyond the cosmic horizon, their light red-shifted into invisibility. The pattern remains, but the lights grow dimmer with each passing eon. Even so, for now, for this cosmic moment we happen to inhabit, it's a sight of extraordinary, almost overwhelming beauty. Galaxies shimmer like countless lanterns along invisible bridges, clusters glow like vast cities of light, connected by highways of pure gravity. The cosmic web is the ultimate expression of order spontaneously emerging from initial chaos. When astronomers look at this structure stretching across billions of light years, they aren't just mapping where matter happens to be located. They're reading the universe's autobiography, written in 3 dimensions. Each filament, each cluster, each yawning void tells part of the story of gravity's slow, unbroken work across cosmic time. It's the same fundamental force that guides planets around stars, that holds galaxies together in their graceful rotations, that bends the light of distant stars into beautiful arcs. If gravity is the honest pen, then this cosmic web is its grandest drawing, a vast interlaced masterpiece where the visible universe hangs like morning dew on unseen strands of spider silk. And though the web is built fundamentally from darkness, from matter that neither glows nor reveals itself directly, it gleams with the faintest light from billions of galaxies, a reminder that the hidden and the visible are forever entwined, forever dependent on each other, forever dancing together. The shape of the universe is not random, not chaotic, not meaningless. Its beauty isn't some fortunate accident of cosmic chance. It's written in the quiet, patient patterns of gravity and time, traced in light that has travelled across billions of years specifically to tell us how the darkness has shaped everything we know, everything we can see, everything we are. From this vast structure, from this cosmic web spanning the observable universe, the light we cherish takes its cue, revealing the hidden web that holds absolutely everything together in its invisible embrace. Gravitational lensing. When light reveals the dark, light is supposed to travel in straight lines. At least that's what our everyday experience persistently suggests. A beam of sunlight shines through a window and lands cleanly on the floor in a perfect geometric ray. A flashlight beam cuts through evening fog in a tidy, predictable cone. These experiences teach us that light goes straight from source to destination. But out in space, far from the familiar comforts of Earth, things are rarely so obedient or straightforward. Out there in the cosmos, light can bend dramatically, twist into curves, stretch into arcs, and even loop entirely back on itself in stunning Einstein rings. Not because it wants to, not because anything is physically tugging on the photons, but because the very stage it moves through, the fabric of space-time itself, is warped by mass. And in that bending, stretching and distorting of light, we find some of the clearest, most visually stunning evidence that dark matter truly exists. This phenomenon is called gravitational lensing, and it's one of the universe's more elegant and beautiful tricks, a cosmic magic show where the invisible reveals itself through the visible. Imagine for a moment placing a large glass bowl over a detailed photograph of a star field. The light from the stars behind the bowl warps and bends as it passes through the glass. The stars' positions shift, their light stretches into arcs. Some stars appear to be in places where none actually exist. Others grow brighter, their light focused and amplified. Still others appear duplicated, with multiple images of the same star appearing in different positions. In space, massive galaxies and enormous clusters of galaxies act exactly like that invisible glass bowl, bending the light from objects far behind them according to Einstein's equations. To an astronomer with the right instruments, it's like looking through a funhouse mirror that happens to be very, very good at doing physics, distorting images in ways that follow precise mathematical rules. When the gravitational lens is particularly strong, say a massive galaxy cluster containing the mass of 1,000 trillion suns, the effect becomes absolutely dramatic and visually spectacular. Distant galaxies located far behind the cluster can appear as long, graceful arcs of light stretching across the sky, or even as complete rings of light known as Einstein rings, named appropriately after the man who first predicted this extraordinary effect would exist. These cosmic distortions aren't just beautiful photographs for astronomy books. They allow scientists to map the distribution of mass in the lensing cluster with remarkable precision, including, and this is the crucial part, the dark matter that makes up most of it. By carefully studying how light is warped, measuring the angles and intensities, astronomers can reconstruct a detailed picture of the invisible structure doing the warping, like a sculptor working in reverse to determine the shape of a mold from the finished casting. It's worth pausing here to appreciate the poetry of this, because this is one of those moments where nature feels genuinely profound. Light, which cannot interact with dark matter directly in any way, cannot bounce off it, cannot be absorbed by it, cannot see it in any conventional sense, still reveals dark matter's presence perfectly by faithfully following the gravitational paths that dark matter carves through the geometry of space-time itself. In a very real sense, the universe cleverly uses light as ink, sketching the precise contours of the unseen for us to read. Even when the lensing effect is weak, just a subtle stretching or slight shearing of many background galaxies, distortions so small they're barely noticeable in individual images, the statistical pattern adds up powerfully when you analyze thousands or millions of galaxies together. Astronomers can measure this weak lensing over huge areas of the sky, building sophisticated statistical maps of where dark matter must be located based on these tiny distortions. It's delicate science requiring immense care, enormous data sets, and sophisticated analysis. But the reward is extraordinary, a detailed view of the cosmos that no telescope can see directly, a comprehensive map of gravity itself, of how mass is actually distributed throughout the universe, rather than just where the light happens to be. One of the most famous, most dramatic, and most convincing pieces of lensing evidence came from a system known evocatively as the Bullet Cluster, two massive galaxy clusters that collided with tremendous energy about 150 million years ago in a cosmic crash of unimaginable violence. When scientists observed the aftermath of this collision with multiple telescopes across different wavelengths, they found something deeply, fundamentally revealing about the nature of dark matter. The hot gas that makes up most of the visible, ordinary matter in both clusters had slowed down dramatically during the collision, as gas clouds do when they crash together. This gas clumped in the middle of the collision site, glowing brilliantly in X-ray wavelengths as it heated to millions of degrees from the impact. But here's what was astonishing. The bulk of the mass, detected through careful gravitational lensing measurements of how background galaxies were distorted, had passed right through the collision site entirely. It ended up well ahead of the bright gas clouds, separated by millions of light years, as if something massive and invisible had ghosted straight through the wreckage while the visible matter slowed and piled up. This separation between light and gravitational mass was stunning in its clarity. If gravity were due only to the visible matter we can see, both the X-ray glowing gas and the gravitational lensing pattern should have lined up perfectly in the same location. But they didn't, not even close. The lensing revealed unmistakably that most of each cluster's gravitational pull came from something that didn't interact with the gas clouds at all, something completely invisible, utterly collisionless, and absolutely dominant in mass. It was as if two invisible ghosts had serenely drifted past one another, completely unaffected, while the visible debris and gas clouds crashed, slowed, and piled up between them. The bullet cluster became a kind of smoking gun for dark matter's existence, a cosmic experiment written clear across millions of light-years of space for anyone with telescopes to see and analyze. It showed definitively that dark matter behaves fundamentally differently from ordinary matter, gliding effortlessly through collisions, rather than heating up, slowing down, or interacting in any electromagnetic way. And because gravitational lensing traces mass, regardless of what form that mass takes or what it's made of, it provided one of the clearest, simplest, most direct proofs that the universe's mass simply is not located where the light is. The invisible outweighs the visible by a factor of 6 to 1. Gravitational lensing also serves as one of the most powerful and versatile tools in modern cosmology's toolkit. It lets us weigh galaxies and galaxy clusters like cosmic scales, revealing the true heft behind the visible glow. When astronomers map lensing patterns across vast regions of the universe, they can even test how cosmic structure has grown and evolved over billions of years. Light that has traveled for 10 billion years carries within it subtle distortions, a snapshot of what the universe looked like when it was much younger. Each tiny distortion in that ancient light is a small but precious clue in a much larger puzzle about how the cosmos has evolved from past to present. These measurements have become so incredibly refined, so precise, that they can now distinguish between different theoretical kinds of dark matter. Cold dark matter, the slow-moving variety that most cosmologists favor, produces the large-scale cosmic web structure we actually observe in simulations and sky surveys. Warm or fast-moving dark matter would smear out that structure significantly, leading to a distinctly different, measurably different pattern of gravitational lensing. So, by reading the faint handwriting of bent and distorted light with ever-increasing precision, scientists can progressively narrow down what kind of invisible matter must exist and what properties it must have. And while the term lensing might sound abstract or technical, the actual images are surprisingly visual and often breathtakingly beautiful. Astronomers regularly publish stunning images showing massive galaxy clusters surrounded by multiple graceful arcs of blue or red light, distant galaxies distorted by the cluster's immense gravity. In some remarkable cases, a single background galaxy is copied several times across the sky by the lensing effect, its light taking multiple different curved paths around the intervening mass, so its images appear arranged in a circle or stretched into shimmering luminous streaks. Each image shows the same galaxy at slightly different times in its history, because the light paths have different lengths. Nature, it turns out, has been running its own telescope all along, a gravitational telescope vastly bigger and more powerful than anything we could ever build, and it's been operating since the universe began. There's even a delightful irony running through all this. We use light, which dark matter refuses to produce or reflect, which passes through dark matter, without the slightest interaction, to map and study dark matter's distribution throughout the cosmos. The very thing dark matter fundamentally avoids becomes our greatest ally in uncovering it. Light's inherent flexibility, its willingness to bend and curve through warped space-time, becomes a form of cosmic honesty. Wherever light's path deviates from a straight line, we know with absolute certainty that something massive is pulling it aside, curving the very space through which it travels. It's tempting to imagine the universe as thoroughly filled with invisible lenses, like panes of subtly distorted glass scattered everywhere through three-dimensional space. Light from the most distant galaxies passes through these countless lenses on its multi-billion-year journey to reach Earth, subtly twisted and bent by every significant clump of mass it encounters along the way. By the time ancient light finally reaches our telescopes, it carries a layered, cumulative story of gravity, of distance, of invisible structure encountered across cosmic time. The night sky we see with our most powerful instruments is not a perfect, undistorted window into the universe. It's more like a beautiful mosaic constructed from distortions, a portrait painted through innumerable curved panes of gravitational glass. And yet this bending, this distortion, this cosmic funhouse mirror effect is precisely what makes modern astronomy so rich and powerful. Without gravitational lensing, we'd have no way to map the dark matter distribution throughout the universe. We'd be blind to most of the cosmos's mass. Every arc stretching across a deep space image, every subtle smudge, every oddly stretched galaxy is a signature of the invisible mass that shaped its light. Space is, as it turns out, the only place where funhouse mirrors actively help us do better physics rather than confusing our perception of reality. There's something profoundly human about this kind of discovery. We're creatures who depend entirely on light to see our surroundings. Our eyes evolved specifically to detect electromagnetic radiation in a narrow range of wavelengths. And yet, through clever application of physics and mathematics, we found an ingenious way to use that same light to learn about what lies completely beyond its reach. We read the universe by studying its distortions, like skilled archaeologists carefully brushing dust off faint outlines of ancient fossils, reconstructing what existed long ago from subtle traces left behind. And the deeper we look with ever better instruments, the more we realize how elegantly the cosmos maintains its balance between the seen and the unseen. The visible and invisible are thoroughly intertwined in ways that are simultaneously mathematical, physical, and somehow poetic. Gravitational lensing reminds us powerfully that even when light bends, even when images distort, truth itself doesn't bend. It's just refracted, temporarily obscured, waiting patiently to be carefully untangled by curious minds and precise instruments. The arcs and rings scattered across our deepest space images, visible in photographs taken by Hubble and other great telescopes, aren't imperfections or flaws in our observations. They're the universe speaking to us in the elegant language of geometry and gravity, if only we learn to listen. And if you trace that language far enough back in time, following these subtle bends in light as it stretches across billions of years of cosmic history, you eventually find that the same gentle distortions, the same telltale signs of dark matter's presence, appear even in the earliest surviving glow of the cosmos itself. The faint afterlight of the Big Bang, still rippling faintly with the fingerprints of darkness pressed into light at the moment of creation. The free electrons wandering through space finally settled down and joined permanently with protons to form neutral hydrogen atoms, the simplest and most abundant element in the cosmos. And with that seemingly simple change, for the first time in the universe's young history, light could finally travel unobstructed through space, racing outward across the expanding cosmos like ripples, spreading from a stone dropped into an infinite pond. That light has been traveling ever since, for nearly 14 billion years, stretching and fading gradually as the universe expanded around it, until today it reaches us as a faint, nearly uniform glow of microwave radiation known as the cosmic microwave background, or CMB, the oldest light in existence, the afterglow of creation itself. If you tune an old television between channels and see static dancing across the screen, a tiny fraction of that visual noise, about 1%, is actually this ancient signal, the whisper of the Big Bang itself reaching your living room. It's everywhere around us, surrounding Earth, flowing through every corner of the cosmos like an invisible sea of ancient photons, a gentle echo from when the universe took its very first deep breath and became transparent. To the naked eye, if we could somehow see microwave radiation, the cosmic microwave background would look perfectly uniform, a smooth, even glow in every direction, the same temperature everywhere you looked. But when astronomers began to study it in exquisite detail, using sensitive instruments launched into space, far above Earth's interfering atmosphere, they discovered something extraordinary, something that would reshape our understanding of the universe's history. There were tiny variations in its temperature, mere thousandths of a degree, scattered across the sky like the faintest freckles on pale skin. These delicate ripples were nothing less than the fingerprints of the early universe, and they contained within them a complete map of everything that was to come in the following billions of years. In those small temperature differences, those barely there fluctuations, we can read the first hints of cosmic structure taking shape, the slightly warmer spots, where the radiation is a tiny bit hotter, were regions where gravity had already begun to gather matter into denser concentrations. Over the following billions of years, spanning an almost incomprehensible stretch of time, those spots would slowly, patiently grow into galaxies, then galaxy clusters, and eventually the vast filaments of the cosmic web we observe today. The slightly cooler areas, the cosmic cold spots, would become the great voids between the filaments, those enormous empty regions where galaxies are rare and space seems almost perfectly empty. It was as if the universe had left us its baby picture, a photograph taken when it was just 380,000 years old, showing the first subtle stirrings of structure, the first hints of everything we see today. Every galaxy, every star, every planet traces its origin back to those tiny ripples imprinted on the cosmic microwave background. But here's the remarkable, crucial part that connects directly to our story of dark matter. Without dark matter's invisible presence, those ripples could never have grown large enough, quickly enough, to form the galaxies we observe. The physics simply doesn't work without it. Visible matter, ordinary atoms made of protons, neutrons, and electrons, were still tightly coupled to light at that time in the universe's history, buffeted around like dust motes caught in brilliant sunlight. Every time gravity tried to pull the ordinary matter together into denser clumps, radiation pressure from all those photons would push it forcefully back out, scattering it again. It was like trying to build a sand castle, while ocean waves kept washing over it. Dark matter, on the other hand, didn't care about light at all. Photons passed through it without any interaction, without slowing it down or pushing it around. It wasn't part of the electromagnetic chaos, wasn't caught up in the light's turbulent dance. While the visible matter was bouncing around like popcorn in a hot pan, unable to settle, dark matter was already pooling quietly under gravity's patient pull, forming the first invisible wells and concentrations that would eventually become galaxy halos. In a very real and profound sense, dark matter gave the universe its essential head start on structure formation. It was the quiet scaffolding being constructed in the dark while ordinary matter was still too hot and energetic to do anything useful. It laid the foundation upon which everything else could eventually gather and build. Those first faint ripples in the cosmic microwave background, those subtle variations in temperature, weren't just random fluctuations in radiation. They were the gravitational fingerprints of dark matter already shaping the cosmos, already pulling matter into patterns, already defining where future galaxies would form billions of years later. Astronomers have been studying that ancient light with increasing precision for decades now, using increasingly sophisticated satellites and instruments. Missions like COBE in the 1990s first detected the ripples. WIRMAP in the 2000s mapped them in greater detail, and the Planck satellite, launched in 2009, painted the most precise portrait yet of the early universe. Each successive mission has revealed the cosmic microwave background in ever sharper focus, like progressively cleaning an old painting to reveal details that were always there but hidden beneath layers of grime. When plotted as a map, the microwave background resembles a mottled sphere of subtle color shifts, warm reds and oranges, where the radiation is slightly warmer, cool blues and purples where it's slightly cooler. To the untrained eye, these variations look like random noise, like television static translated into color. But they're anything but random. They reveal with extraordinary precision the universe's exact recipe, its fundamental composition. How much of it is ordinary matter? How much is dark matter? How much is dark energy? What is the rate of expansion? How old is the universe exactly? What is its geometry? All of these profound questions have answers written in those subtle temperature fluctuations. From careful analysis of those ripples, scientists have calculated with remarkable confidence that only about 5% of the universe is made of ordinary atoms. The stars, the planets, the gas clouds, everything we've ever touched or seen with our eyes or detected with electromagnetic telescopes. About 27% is dark matter, that invisible substance we've been exploring throughout this journey. And the remaining 68% is dark energy, that even more mysterious force that drives the universe's expansion to accelerate rather than slow down over time. Those numbers aren't vague guesses or rough estimates. They're measured directly from the cosmic microwave background, precise to within a few percentage points, written clearly in the subtle pattern of its temperature fluctuations across the sky. It's as if the universe left us a detailed accounting ledger carved into its oldest surviving light, a complete inventory of everything that exists. To imagine what those ripples represent more tangibly, picture a perfectly still pond just before sunrise. The first faint light of morning touches its surface, and you notice small, concentric circles spreading outward across the water, soft, gentle, barely visible. Each ripple marks a moment when the water remembered a disturbance, a leaf dropping from a tree, a fish breaking the surface, a breath of wind touching down. Now scale that image up to the size of the entire observable universe, and you have a sense of what the cosmic microwave background shows us. Those ripples represent the universe remembering its own beginning, its own birth, and they're astonishingly precise in what they tell us. The spacing between the peaks and troughs of those fluctuations, the amplitude of the variations, the specific pattern they form, all of these details depend on exactly how much matter and radiation the universe contained in its youth. It's like listening to the echo of a bell, and being able to infer not just that a bell rang, but its exact size, shape, composition, and how hard it was struck. From this ancient echo, scientists can tell not only what the universe was made of at that time, but how it has evolved ever since. How structure formed, how galaxies assembled, how the cosmic web took shape. Perhaps most poetically, this ancient light is still arriving constantly. Every second, photons that have traveled for nearly 14 billion years wash over Earth, carrying with them an indelible memory of the cosmos before the first star was born. They pass through you, through the atmosphere, through buildings and mountains, endless waves from the time when everything began, still reaching us, still telling their story. It's profoundly humbling to realize that every image of a galaxy, every map of cosmic structure, and every simulation of dark matter's role in shaping the universe all trace back ultimately to this faint background glow. It's the baseline, the foundation, the fundamental reference point for all of cosmology. The quiet hum beneath all cosmic music. Even the tiniest irregularities in that glow, variations so small they seem almost insignificant, are crucial to everything that exists. Without them, the universe would have no structure at all. If the cosmic microwave background had been perfectly uniform, with no variations whatsoever, gravity would have had no starting point, no seeds to work with. Matter would never have gathered into clumps, stars would never have ignited, galaxies would never have formed. The night sky would be a smooth, featureless, eternal fog. The tiny imperfections, those 1 in 100, 000 temperature differences, are literally the origin of all structure, all complexity, all beauty in the cosmos. Imperfection, in this profound case, is the origin of everything interesting, everything wonderful. Every time scientists measure the cosmic microwave background more precisely, using better instruments and more sophisticated analysis techniques, the universe's story becomes clearer and more detailed. And every time we look deeper into that ancient light, the role of dark matter grows more evident and more essential. It was dark matter, that silent partner, guiding structure formation before ordinary matter could even participate, before light could speak for itself or be used as a tool of astronomy. The galaxies that now shine brilliantly across the night sky are simply the glowing outlines, the luminous tracings of shapes that dark matter drew first in invisible ink billions of years ago. The cosmic microwave background is, in many profound ways, the universe's autobiography, written in the faintest possible radiation. It tells of a hot, dense youth, of gradual, patient cooling, of invisible forces quietly at work long before light could roam free through space. And though the universe has grown immeasurably since that time, expanded to proportions almost beyond comprehension, those early ripples still echo through everything that exists today. Through every star born in a nebula, through every planet condensed from a protoplanetary disk, through us creatures made of atoms forged in stellar cores, standing on a rocky planet, looking up at the night sky, and wondering about our cosmic origins. The next time you glance at the stars on a clear night, far from city lights, remember that you are seeing the end result of a long story that began in that ancient light. Those faint ripples on the cosmic microwave background's surface, like ripples on a vast pond, eventually became galaxies, stars, planets, and life itself. The echo from the beginning still hums softly all around us, constantly arriving from every direction, carrying the quiet memory of how darkness gave essential shape to the light, how invisible matter laid the foundation for everything visible. Building galaxies, the potter's invisible hands. By the time the universe was a few 100 million years old, still incredibly young by cosmic standards, a toddler in the grand timeline, the brilliant fog of the cosmic microwave background had faded into the distance, redshifted by expansion into longer wavelengths that no longer illuminated space. Darkness ruled the cosmos once again, but this was not an empty, barren darkness. It was a darkness full of invisible structures already forming beneath the surface, preparing for what would come next. In that unseen landscape, gravity had been extraordinarily busy sculpting the future with patient, invisible hands. Dark matter had already begun clumping together long before the first stars would ignite. Freed from the push and pull of light, unaffected by radiation pressure or electromagnetic forces of any kind, it drifted and gathered under its own quiet gravity, forming enormous halos, vast, roughly spherical cocoons of invisible matter spreading through space. Each halo was a gravitational seed, a depression in the fabric of space-time, a potential home for the luminous galaxies yet to come. If you could have somehow seen the universe at that time, with eyes sensitive only to dark matter's presence, you'd have witnessed a cosmos filled with ghostly spheres of varying sizes, completely dark yet absolutely brimming with gravitational potential. Into these carefully prepared halos, ordinary matter, the atoms that make up everything we can see and touch, began to fall like rain into valleys. Clouds of hydrogen and helium gas, the simplest elements forged in the Big Bang itself, began cooling as they collapsed into the gravitational wells carved out by dark matter over millions of years. As the gas sank deeper into those invisible gravitational wells, following paths carved by dark matter's patient accumulation, it began to swirl from angular momentum. It couldn't shed. It compressed under its own weight. It fragmented into denser knots. And where the compression became strong enough, where density and temperature reached critical thresholds, the first stars flickered to life, igniting in the primordial darkness like embers, catching and kindling, like lights gradually turning on in a vast dark house. In a genuinely poetic sense, dark matter was the invisible potter, shaping vessels on a cosmic wheel, and the visible universe was the clay being formed. Dark matter shaped the molds, supported the structures, and steadied everything while never once showing its own hidden hand. Without the patient guidance of dark matter preparing the ground, this process of galaxy formation would have been dramatically slower, far messier, and much less efficient. Ordinary matter, left to its own devices, couldn't have gathered quickly enough to form galaxies in the abundance we observe. The night sky might be a far lonelier, emptier place, a vast dark canvas with only a handful of small, faint galaxies scattered across cosmic distances. The halos themselves formed in a beautiful cosmic hierarchy that scientists can now trace through sophisticated simulations. Small halos appeared first in the young universe, gravitationally attracting their neighbors over time, and merging to create progressively larger and larger structures through billions of years. When two halos collided and combined, their dark matter passed through each other almost completely unhindered, like ghosts walking through walls, barely noticing the collision, combining smoothly to form a new, more massive gravitational home for galaxies to grow and thrive within. Meanwhile, the visible gas, collisional, chaotic, messy, heated up dramatically from the collision, shocked into brilliant emission, and then cooled again over millions of years, often sparking intense new bursts of star formation in the process. Over billions of years of cosmic time, this cosmic dance of merging and growth built everything we see today, from the smallest, faintest dwarf galaxies containing only millions of stars, to the giant spirals and massive ellipticals that contain hundreds of billions of suns. Every galaxy you can see through any telescope, including our own Milky Way, sits at the heart of one of these invisible dark matter halos. The stars and planets, the glowing nebulae and brilliant quasars, everything visible, is just the decorative frosting, the beautiful surface decoration on a vast dark foundation that extends far beyond where any light shines. The halo extends dramatically far beyond the luminous disk of a galaxy, reaching hundreds of thousands of light years into the surrounding void like an invisible atmosphere. Most of its mass lies where light can never go, where no telescope can directly see, where only gravity's effects reveal its presence. Computer simulations of cosmic structure formation beautifully reveal this fundamental pattern. When astronomers model the growth of structure over cosmic time in their supercomputers, they often start with nothing but dark matter particles and the laws of gravity, deliberately leaving out stars and gas at first to see what dark matter alone creates. Out of this elegant simplicity, halos emerge spontaneously, inevitably, clustering and merging in intricate patterns that grow more complex with each passing simulated eon. When gas physics is added later to the model, when ordinary matter is allowed to respond to the dark matter's gravitational landscape, the luminous material naturally gathers within the dark scaffolding that's already formed, creating galaxies that look strikingly, remarkably similar to the real galaxies we observe through our telescopes. It's as if the universe naturally, inevitably, builds from the shadows outward. The dark matter sets the mold first, defines the container, establishes the structure. The light then fills it in, decorating the invisible framework with visible beauty. It's a strangely comforting idea when you really contemplate it. For all our natural human focus on light, on stars and nebulae and glowing galaxies, on everything we can photograph and admire, the universe's true architecture, its fundamental structure, belongs to the unseen. The halos are like invisible hands shaping clay in the dark, patiently guiding where galaxies may grow, and precisely how they will evolve over cosmic time. Even the grand, graceful spirals of our Milky Way owe their elegant form to this hidden influence. Without the gravitational stability provided by its massive dark halo, the delicate spiral arms of our galaxy might gradually unravel over billions of years, stars drifting apart like autumn leaves scattered by wind, structure dissolving into chaos. Dark matter's persistent gravitational pull not only gathered gas in the first place, enabling star formation, but also determined the fundamental rhythm and pace of star formation throughout cosmic history. In dense regions where halos formed quickly and merged frequently, galaxies became crowded and extraordinarily bright, burning through their available gas in rapid, intense bursts of star birth that lit up the early universe. In quieter corners of the cosmos, in regions less dense, where halos grew more slowly and mergers were rare, star formation stretched out leisurely over many billions of years, producing galaxies with gentler, more drawn-out histories, galaxies that are still forming stars today, billions of years after the universe began. The cosmic web itself, with its intricate filaments and dense nodes we discussed earlier, acted as a kind of highway system, connecting these halos across vast distances. Gas flowed steadily along those filaments like rivers following valleys, feeding the growing galaxies continuously. Each halo was positioned like a basin at the junction of those cosmic streams, collecting material patiently and turning it gradually into light through the alchemy of star formation. The result was a universe both orderly and vibrantly alive, a grand interplay of gravity, motion, gas dynamics, and deep time playing out across billions of years. Even today, in the present epoch, billions of years after the first stars formed, the relationship between dark matter and visible matter continues to actively shape how galaxies evolve and behave. The halos dictate how fast galaxies spin on cosmic timescales. They determine how massive galaxies can grow before feedback from star formation or black holes halts their growth. They influence how galaxies interact with their neighbors through gravitational tugs across millions of light years. When galaxies collide in those spectacular mergers we can photograph with our best telescopes, it's their dark matter halos that meet first, long before the visible disks of stars ever touch, merging over hundreds of millions of years in a slow gravitational ballet. The luminous mergers we observe and admire, those spectacular collisions captured by Hubble and other great telescopes, are merely the visible surface expression of a deeper, darker event happening quietly beneath, an invisible dance of dark matter halos combining into larger structures. Astronomers have even found compelling hints of dark matter's influence operating on the smallest scales of galaxy formation. Tiny dwarf galaxies orbiting giant systems like the Milky Way appear to be held together primarily by dense knots of dark matter at their cores. Without that invisible gravitational glue, their weak gravity wouldn't be nearly enough to prevent tidal forces from tearing them apart as they orbit through the outer regions of larger galaxies. In a very real sense, dark matter acts like cosmic glue, preserving these delicate, fragile structures that would otherwise quickly dissolve into scattered stars. If dark matter somehow didn't exist, if we could magically remove it from the universe's history, the cosmos would be utterly, completely unrecognizable to us. The early gas after the Big Bang would have remained almost evenly spread through space, unable to condense quickly enough into the dense knots necessary for star formation. Galaxies, if they managed to form at all under such conditions, would have been dramatically smaller, far rarer, and much dimmer, faint smudges barely visible against the cosmic darkness. The night sky might contain only a few dozen faint galaxies visible to our instruments, rather than the hundreds of billions we actually observe filling the universe. The dark, it turns out with poetic irony, made all the light possible. There's also something deeply poetic about the timing of when galaxies first formed. The first generation of stars to ignite inside those primordial dark matter halos likely lived fast and died spectacularly young, as the most massive stars always do. They burned with incredible heat and intensity, flooding the surrounding universe with torrents of ultraviolet light that slowly burned away the lingering neutral hydrogen fog that still pervaded space, rendering the universe transparent in a process called reionization. When those first massive stars died in catastrophic supernova explosions, they scattered newly forged heavy elements, carbon, oxygen, nitrogen, iron, and dozens of others, into the surrounding space. Those elements, created in stellar cores and supernova fires, later became the essential building blocks of planets, of life, of everything complex and interesting in the universe. In that profound way, the unseen sculptor didn't just shape the galaxies themselves, it set the entire stage for everything that would one day emerge to wonder about its own existence, to look up at the stars and ask questions about origins. Astronomers continue to refine their understanding of how these dark matter halos evolve over cosmic time, using ever better simulations and ever deeper observations. They measure carefully how galaxies move within their halos. They track how gas flows through them across billions of years. They study how halos grow through mergers and accretion. The details grow increasingly complex as our instruments improve and our simulations become more sophisticated, but the underlying story remains elegantly, beautifully simple. Where dark matter gathers first, light inevitably follows. The halos form the invisible gravitational wells, deep depressions in space-time. The stars are merely the bright reflections glittering on their surfaces. Sometimes, when you look at a photograph of a distant galaxy, perhaps the majestic Andromeda galaxy glowing softly against the infinite black, or the Whirlpool galaxy with its graceful spiral arms, it's easy to forget that most of what holds it together, most of what gives it structure and stability, cannot be seen in any wavelength of light. The stars trace those beautiful photogenic spirals that grace astronomy textbooks and planetarium shows, but the fundamental shape of the structure, the reason those spirals exist at all, is determined by something much larger, much quieter, and profoundly mysterious, the dark matter halo surrounding and permeating everything. Every rotation of those spiral arms, every flicker of light from a newborn star, every supernova explosion is a living testament to that hidden framework providing gravitational structure. If you could somehow strip away all the stars and glowing gas with a cosmic eraser, removing every visible component, you'd still see the galaxy's true form revealed, a dark, massive halo extending far beyond the edges of what any telescope can photograph. A form shaped by gravity alone, sculpted patiently over billions of years of cosmic time, and still growing ever so slowly even now as smaller halos merge into it. Dark matter doesn't build in haste or with fanfare. It doesn't shine or announce itself proudly, but it holds everything in its steady, invisible grasp, shaping the luminous universe like a master potter molding clay, by touch alone in absolute darkness, creating beauty without ever seeing the finished work. The galaxies scattered across the cosmos are its art, delicate, enduring and beautifully balanced against the void. And though dark matter itself will never be seen directly, its fingerprints are pressed gently, unmistakably into the light of every single star that has ever shone. Our galaxy's invisible ocean. Our Milky Way galaxy is a familiar, even comforting sight, a great glowing river of stars flowing across dark summer skies, a magnificent spiral with sweeping arms that shimmer with the light of hundreds of billions of suns. When we look up on clear nights far from city lights, we're seeing our cosmic home from the inside, edge-on, a cross-section through the galactic disk. But that glittering view, as beautiful as it is actually a little misleading. What we see with our eyes and photograph with our cameras is just the bright, photogenic surface of something far larger, far more massive, and infinitely quieter than those visible stars suggest. The Milky Way is not merely a disk of stars and glowing gas, not simply the spiral structure we see in artists' renderings and scientific illustrations. It's enveloped completely in an immense invisible halo of dark matter that stretches hundreds of thousands of light years beyond what any telescope can possibly capture or photograph. We live deep inside this halo, completely surrounded by it on all sides. Every atom in your body, every photon of starlight entering your eyes, every spacecraft humanity has ever launched, every drifting comet at the solar system's edge, all of it is moving through this vast, unseen ocean of dark matter that permeates our entire galaxy. It doesn't physically collide with us or leave any trace we can feel with our senses. There's no wind from it, no resistance, no friction, not even the faintest ripple in the air we breathe. Yet its gravity quietly, constantly shapes the orbit of our sun around the galactic center, influences the paths of planets, and affects the movement of every star we can see in the night sky. It is the invisible stage, the unseen foundation upon which the Milky Way performs its ancient cosmic dance. The sun itself is not sitting still within the galaxy, not fixed in place like a landmark. It's racing through space at an astonishing speed, moving at roughly 220 kilometers every second. That's nearly 500,000 miles per hour. At that tremendous velocity, it takes approximately 230 million years for our solar system to complete one full orbit around the galactic center. To put that in perspective, the last time the sun was in this exact position in its galactic orbit, dinosaurs had only recently begun to dominate Earth. We're on a cosmic merry-go-round that moves so slowly that civilizations rise and fall, species evolve and go extinct, continents drift across the planet's surface, all within a tiny fraction of one galactic year. As our solar system moves through the galaxy, it's simultaneously gliding through the Milky Way's dark matter halo, passing through an invisible current that stretches in every conceivable direction around us. You might imagine our solar system as a small ship sailing steadily across a calm ocean. The dark matter doesn't push the ship or pull it directly, doesn't create waves or cause storms, but it gently defines the contours of the sea. The ship travels across the gravitational landscape through which everything moves. This unseen halo is absolutely colossal in scale. If you could somehow make dark matter visible to your eyes, rendering it in some glowing wavelength you could perceive, you'd see a faint spherical glow enveloping our entire galaxy, reaching well beyond the bright spiral arms we see in photographs, extending far past the furthest visible stars of the galactic disk. It would stretch past even the distant globular clusters that orbit the Milky Way's outer regions like fireflies circling a distant campfire. Within this enormous bubble of dark matter, our visible Milky Way, all its brilliant stars, glowing nebulae, and bustling stellar nurseries, sits like a small bright candle positioned carefully in the exact center of a vast glass sphere, hundreds of thousands of light years across. For astronomers, mapping this invisible halo is like trying to chart the depths of an ocean you cannot see using only the motion of ships sailing across its surface. They can't observe the dark matter directly, can't photograph it or detect its particles, but they can meticulously observe how stars move under its gravitational influence. The way those stars orbit, the speeds they achieve, how their paths curve and drift, all of this reveals the shape and distribution of the underlying dark matter mass. Much like tracking the movement of seaweed or floating debris, tells you how underwater currents flow, even when the water itself is murky and opaque. One of the most beautiful and useful tools for this kind of detailed study comes from stellar streams, long, graceful trails of stars that wind their way across the sky like cosmic ribbons. These streams form through a kind of gravitational tragedy when small galaxies or tightly bound globular clusters venture too close to the Milky Way's powerful gravitational pull. Over millions of years, our galaxy's tidal forces gradually tear these smaller systems apart, pulling them to pieces. The stars that once orbited together in those doomed satellite galaxies spill out along their orbital paths, stretching into luminous ribbons and arcs that can wrap entirely around our galaxy multiple times. Each stream traces a specific path shaped by the dark matter halo's gravitational contours, curving and twisting according to its invisible, complex geometry. By studying these streams in detail, measuring their positions and velocities with precision, astronomers can map the gravitational landscape around the Milky Way in remarkable, increasingly fine detail. It's as though the galaxy's invisible skeleton, its true underlying structure, is being revealed through these glowing fractures, these scars of ancient mergers, beautifully illuminated by the scattered stars that escaped destruction. The most famous and well-studied of these stellar streams is the Sagittarius stream. The stellar remains of the Sagittarius dwarf galaxy, a small satellite galaxy currently being absorbed, devoured really, by our much larger Milky Way. Its long, graceful arc of stars wraps around us like a ghostly ribbon made of scattered suns, whispering silently of gravitational encounters that happened hundreds of millions of years ago, long before humans evolved, before complex life emerged, before Earth's continents assumed their current configurations. From careful observations of this stream and others like it, we now know with considerable confidence that the Milky Way's dark matter halo isn't perfectly smooth and uniform. It has real structure, dense knots where dark matter has concentrated, gentle gradients where density changes, and subtle ripples in its distribution caused by ancient collisions with other galaxies. It's a powerful reminder that even the supposedly smooth dark matter is actually dynamic, constantly evolving and shifting over cosmic time. Each passing satellite galaxy that gets too close leaves a persistent fingerprint in the halo, a gravitational ripple in the dark matter distribution that can last for billions of years, slowly fading but never completely disappearing. Though we drift continuously within this vast unseen realm, dark matter does not touch us in any conventional physical sense. Its particles, whatever they ultimately turn out to be, pass effortlessly through the Earth, through your body, through the walls of your home, through solid rock and steel, without ever interacting electromagnetically, without ever leaving any detectable mark. Right now, at this very moment, trillions upon trillions of dark matter particles may be passing through your body every single second, streaming through you like you're not even there, and yet you wouldn't know it, wouldn't feel even the slightest sensation. There's no tingle, no warmth, no weight, nothing. It's an idea that feels genuinely eerie at first, perhaps unsettling, but really, when you get used to it, it's quite peaceful in its own way. The dark matter ocean doesn't disturb us, doesn't interfere with our lives, doesn't affect our daily existence in any noticeable way. It simply carries us along in its immense, patient gravitational flow as our solar system orbits the galaxy over hundreds of millions of years. The halo's gravity is what keeps our Milky Way stable and coherent. It ensures that stars near the outer edge of the galaxy, hundreds of thousands of light years from the center, orbit just as securely and predictably as those near the crowded galactic core. Without that invisible gravitational scaffolding holding everything together, the outer regions of our galaxy would gradually drift away, dissolving into intergalactic space like smoke dissipating on a breeze. The dark matter halo is the quiet anchor, the unseen foundation that holds our entire galaxy together across billions of years, the invisible companion to all the brilliant photogenic light. Astronomers are still actively learning about the halo's exact three-dimensional shape, refining their models with each new observation and simulation. Some evidence suggests it may be slightly flattened, shaped more like a sphere pressed gently at the poles than a perfect ball. Others think it might be subtly lopsided, warped somewhat by ancient merger events, or perhaps by the ongoing gravitational influence of the nearby Andromeda galaxy, which is itself approaching us for an eventual merger billions of years in the future. Whatever its precise shape turns out to be, one thing is absolutely certain: The halo defines the true size of our galaxy, a size far, far greater than the delicate spiral structure we can photograph with our most powerful telescopes. The dark matter halo also acts as a kind of gravitational safety net, catching and retaining smaller galaxies that pass too close to the Milky Way. Many of the faint satellite galaxies orbiting our own tiny, dim smudges of light, barely visible even through professional telescopes, owe their continued existence entirely to the halo's persistent invisible pull. Without it, they would have been stripped away or scattered long ago. Over cosmic time, some of these satellites will spiral gradually inward, eventually merging completely with the Milky Way, feeding its growth and thickening its dark matter halo even further, in a process that's been ongoing for billions of years. The galaxy we live in, our cosmic home, is still assembling, still changing, still growing. Its structure continues to be slowly, patiently sculpted by the quiet gravity of dark matter, acting across eons of time. It's genuinely humbling to realize that every orbit we observe, from the Sun's grand 230 million year circuit around the galaxy to the smallest dance of stars in a distant cluster, is ultimately guided by this unseen gravitational hand. We often talk casually about space as being empty, as vacuum, as void, but in truth, we are constantly swimming in a sea of invisible substance that neither glows nor resists our passage. A vast gravitational ocean whose subtle currents define absolutely everything we see around us. When you look up at the Milky Way stretched across a dark summer sky, that glowing band of countless stars, remember that what you're seeing is just a thin, luminous layer floating atop something vastly larger and more massive. We're not outside observers admiring the galaxy from afar. We're integral parts of this structure, drifting quietly within it, embedded in its invisible heart. The halo doesn't end at some distant edge beyond our view. It surrounds us completely, envelops us on all sides. We're inside it right now, have been for the entire existence of our solar system, will be for billions of years to come. Dark matter gives our Milky Way its fundamental shape, its long-term stability, and its impressive longevity spanning billions of years. It is the reason our sun follows its steady, Chapter 6, the cosmic microwave background massive echo of creation. Long before there were stars scattered across the night sky, before galaxies began their ancient spiral dances, before even atoms as we know them could stably exist, the universe was filled with something very different from what we see today, a hot, dense, brilliant fog of particles and light all tangled together in a cosmic dance of energy. It was a place fundamentally without transparency, a universe so thick with matter and radiation that nothing could be seen beyond arm's length. If anyone had been there with arms and eyes, it was a cosmic dawn before dawn itself, before the first sunrise, before the concept of day had any meaning. Photons, those fundamental particles of light that now stream freely through space, allowing us to see distant galaxies, couldn't travel even a short distance without constantly colliding with free electrons and protons in a restless, energetic dance. If you could have somehow stood in that ancient primordial fire and looked around, you wouldn't have seen anything at all, despite the intense energy. The universe wasn't dark exactly. It was blinding, but opaquely so, like being inside a star, surrounded by light yet unable to see through it. But as the universe expanded relentlessly outward, driven by the momentum of its explosive birth, it gradually cooled. And when it cooled enough, when the temperature dropped below a critical threshold about 380,000 years after the Big Bang, a cosmic blink of an eye in the grand scheme, but an eternity by human standards, everything changed in a moment. Cosmologists call recombination. The free electrons wandering through space finally settled down and joined permanently with protons to form neutral hydrogen atoms, the simplest and most abundant element in the cosmos. And with that seemingly simple change, for the first time in the universe's young history, light could finally travel unobstructed. Welcome to the Sleepy Professor, the hidden universe. Tonight, as you settle into the gentle embrace of evening and let the weight of the day dissolve like mist at dawn, we're embarking on a journey into one of existence's most profound mysteries. We're going to drift through the cosmos, exploring the invisible substance that binds everything together, a cosmic glue so fundamental that without it, the universe as we know it simply wouldn't exist. It's called dark matter, and though it makes up most of the cosmos, filling every corner of space like an invisible ocean, we've never actually seen it, not even once. So, if you're ready, dim the lights around you, take a slow deep breath, feel your shoulders drop, and let's drift gently into the dark matter of space, where the greatest secrets hide in plain sight. The frozen sentinels of Antarctica. Even in Earth's most desolate corner, scientists keep watch. The Ice Cube Neutrino Observatory stands as proof of humanity's dedication to listening rather than shouting at the universe. Beneath a full cubic kilometer of pristine Antarctic ice, thousands of sensors wait in profound darkness. The ice entombing them is older than written history, compressed over millennia into crystal perfection. In that frozen sanctuary of absolute quiet, scientists created one of the most sensitive listening posts ever imagined. This isn't merely about patience, it's about understanding silence as a language of its own. The quiet isn't empty, it brims with meaning. Each day without a signal teaches scientists something invaluable they couldn't learn otherwise. Every null result narrows the possibilities, refining the profile of what dark matter could be, its mass, its interactions, its nature. Imagine a sculptor working in reverse. Rather than adding clay to reveal form, scientists remove possibilities, chipping away at what dark matter cannot be until only truth remains. Science advances not just through eureka moments, but through careful elimination. It's an elegant dance of negation, and dark matter has been remarkably generous with its silence. That silence is data, precious, illuminating, and strangely beautiful in its own right. Yet this silence doesn't breed discouragement. For many physicists, the pursuit itself holds the magic. Somewhere, on some ordinary night when the world has forgotten to watch, a detector will finally stir. A minuscule flicker will appear on a screen, and humanity will realize it has heard the universe breathe in an entirely new way. That moment, when it arrives, will justify every patient year. There have been false dawns before, tantalizing glimpses that seemed like breakthroughs. A few experiments reported potential signals over the years, brief flashes and unexpected patterns, only for deeper analysis to reveal mundane explanations or cast doubt. Imagine the emotional journey, the initial surge of discovery, hearts racing, followed by meticulous testing that so often leads back to the familiar embrace of not yet. But this is how authentic science unfolds, not dramatically or instantaneously, but carefully, methodically, honestly. Each false lead teaches something new, refines instruments, sharpens expectations. Even empty results shape our understanding of what's possible and what remains to explore. This is discovery's unglamorous face, the side requiring faith not in certainty, but in the process itself, in the patient unfolding of truth. The human dimension of discovery. What's beautiful about this search is its profoundly human dimension. The scientists who tend to these detectors are not working in grand control rooms filled with flashing lights or dramatic observatories perched on mountain peaks. They're often alone, surrounded by rock and quiet machinery, maintaining a watch that might last decades. Some spend months at a time in underground laboratories, seeing the same walls, hearing the same hum of equipment, waiting for a signal that may never arrive in their lifetime. There's a kind of meditative patience to it, a calm trust that borders on faith, They believe the universe is whispering, even if we haven't yet learned how to hear it properly. It's not unlike monks keeping vigil in ancient monasteries, or lighthouse keepers tending their lamps through long, empty nights. The work demands a special kind of courage, not the courage to face danger, but the courage to face the possibility that your life's work might yield only silence. You could think of these experiments as a global symphony of stillness. Each one is a bell waiting to ring, a silent ear pressed against the heartbeat of the cosmos. From deep mines in South Dakota to caverns beneath Italian mountains, from laboratories carved into Canadian nickel mines to facilities hidden under Spanish peaks, the world is dotted with these quiet listening posts, and every once in a while something unexpected flickers, a small burst of light, a trace of movement, and the room holds its breath. Was that it? Was that the touch of the invisible? Was that the moment when the veil between the seen and unseen grew thin enough to pierce? Usually the answer is no. Usually it's a cosmic ray that slipped through the shielding, or a trace of natural radioactivity in the detector materials, or just statistical noise dressed up as a signal. But someday it may be yes. A discovery that would change everything. If that day comes, it will mark one of the most profound discoveries in the history of science, proof that we have directly detected a substance that has shaped the universe since its beginning. We will have caught a particle that doesn't want to be caught, heard the faintest sound in the quietest cathedral. The implications would ripple through physics, astronomy, and our understanding of reality itself. Until then, the detectors keep listening. The lights stay dim, the instruments hum softly in their underground chambers, and the world above goes about its business, unaware of the deep, patient vigil being kept below. People shop for groceries, watch movies, fall in love, argue about politics, all while beneath their feet, in the bedrock of the planet, scientists continue their watch, surrounded by darkness, listening for a single tap in the night. And if we can't catch the invisible particles here on Earth, if the silence continues year after year, then perhaps the answer lies elsewhere. Maybe, just maybe, the sky itself can help us find what the ground has not yet revealed. After all, space is vast, and the universe has been running its own experiments for far longer than we have. Searching the sky, indirect detection. If dark matter particles refuse to reveal themselves in our detectors here on Earth, perhaps they might give themselves away somewhere else, out there in the sky, where the stakes are higher and the stage is grander. After all, the universe itself has been running experiments for billions of years, far longer than any human laboratory. Galaxies collide in slow-motion ballades that take millions of years to complete. Particles interact in the hearts of stars and in the space between them. Vast clouds of dark matter overlap and merge in dances we can barely detect. Somewhere in all that quiet activity, faint traces might appear, little flickers of light where none should be, anomalies in the cosmic background, subtle glows that don't match any known astrophysical source. These would be the fingerprints of the invisible, left behind like condensation on glass. This approach is called indirect detection. Instead of trying to catch a dark matter particle directly, scientists look for its possible byproducts, high-energy gamma rays, positrons, or neutrinos created when dark matter particles collide and annihilate each other. It's a bit like searching for footprints rather than the creature itself, or looking for the wake of a boat rather than the boat. If two invisible particles meet in the perfect conditions and transform into visible energy, the resulting radiation might be the clue we've been waiting for. The galactic center, a prime target. The best places to look are where dark matter is expected to be densest, where gravity has drawn it into concentrated pools. The center of our galaxy, for example, is a prime target. The Milky Way's core is a chaotic, energetic place, packed with stars, gas, dust, and according to all our models, an enormous concentration of dark matter swirling around a supermassive black hole 4 million times the mass of the Sun. If dark matter particles are occasionally annihilating there, colliding in the cosmic crush and transforming into pure energy, the region should glow faintly in gamma rays, the most energetic form of light known, invisible to our eyes, but detectable by specialized telescopes. And indeed, telescopes like NASA's Fermi Gamma Ray Space Telescope have spotted something intriguing, an excess of gamma rays coming from the galactic center that doesn't quite fit what we expect from known sources. For a while, this mysterious glow looked like a perfect candidate for a dark matter signal. The energy spectrum, the spatial distribution, the intensity, all of it matched remarkably well what physicists predicted WIMP annihilations might produce. Excitement grew in the scientific community. Papers were published. Conferences buzzed with speculation. Had we finally found the glow of the invisible? Had dark matter revealed itself, not through a direct collision, but through the light of its own self-destruction? The challenge of cosmic noise. As is often the case in science, the answer was complicated. The signal was real. No one disputed that gamma rays were indeed coming from the galactic center in excess of what simple models predicted. But explaining it turned out to be tricky. The center of the Milky Way is a chaotic place, full of energetic phenomena that make interpretation maddeningly difficult. Pulsars spin like cosmic lighthouses. Black holes beam energy across the void. Cosmic rays accelerate to near-light speeds. Clouds of hot gas radiate across the spectrum. Any of these could mimic the gamma-ray excess. One team would claim the pattern looked exactly like dark matter annihilation, providing detailed models and statistical analyses. Another would argue with equal conviction that it was better explained by an undiscovered population of millisecond pulsars, rapidly spinning neutron stars that could produce similar gamma-ray signatures. It was like seeing fireflies flickering in the distance on a foggy night. Are they real lights or just reflections on the glass? Are we seeing something new or something familiar dressed in unfamiliar clothes? The debate continues to this day. New data refines the picture, but hasn't yet settled the question definitively. That's the challenge of indirect detection. Space is noisy and dark matter. If it's there, whispers beneath the roar. Dwarf galaxies, laboratories in the sky. Beyond our own galaxy, dwarf spheroidal galaxies became the next best hunting grounds. These tiny, faint galaxies orbit the Milky Way like moths around a flame. They're remarkable objects, almost entirely made of dark matter, with only a sparse scattering of stars to reveal their presence. In a sense, they're the purest dark matter laboratories nature has provided. They're simple, quiet systems with little background noise. No supermassive black holes, no vigorous star formation, no complex astrophysics to muddy the waters. If dark matter particles are annihilating anywhere, the clean signature should appear there, like a single flute note in an otherwise silent concert hall. This makes them perfect laboratories for indirect detection. Dozens of telescopes have pointed their instruments toward these dwarfs, listening for the faint hum of gamma rays. So far, the results have been tantalizingly close, but ultimately inconclusive. Occasional hints appear, gentle upticks in the data that make hearts race. But never the solid, unambiguous yes. That would clinch the case. Sometimes the signals seem promising, compelling enough to warrant press releases and follow-up observations. Then new data arrives and smooths them away like footprints in the sand. The universe, it seems, enjoys being coy. Positrons and neutrinos, other messengers. Other experiments search for different byproducts of dark matter annihilation. Some focus on positrons, the antimatter counterparts of electrons, which could be produced when dark matter particles meet their doom. It's an elegant idea. If dark matter annihilates, some of that energy might transform into matter-antimatter pairs that spray out into space. Detectors aboard spacecraft like the AMS-02 experiment on the International Space Station have found curious excesses of positrons in cosmic rays. More positrons than expected are zipping through space, and their energy spectrum doesn't quite match standard astrophysical predictions. Could this be dark matter revealing itself through antimatter? The possibility is tantalizing. But again, interpretation is the challenge. Pulsars and supernova remnants can also produce positrons. Cosmic rays smashing into interstellar gas can create them, and teasing apart those natural astrophysical sources from a potential dark matter signal is like trying to hear a single violin in an orchestra of explosions. The signal is there, but its meaning remains ambiguous. High-energy neutrinos, those ghostly travelers that rarely interact with anything, are another potential clue. If dark matter accumulates in dense regions like the Sun's core, slowly sinking toward the center over billions of years, it might occasionally annihilate there, releasing neutrinos that fly straight out into space, unimpeded by the Sun's crushing mass. Detectors such as IceCube in Antarctica are tuned to listen for them. Enormous volumes of ice, carefully instrumented with thousands of sensors, wired to flash when a neutrino passes through and creates a telltale particle shower. But so far, those searches too have returned silence. No clear excess of neutrinos from the Sun or Earth's core, no smoking gun pointing to dark matter self-destruction. The difficulty of distinguishing signals. The main difficulty with all of these efforts is that space is full of activity, relentless, energetic, and complicated. Cosmic rays bombard everything. Pulsars spin like lighthouses, their beams sweeping across space thousands of times per second. Black holes beam energy across the void in jets that stretch for millions of light years. Supernova remnants expand like cosmic fireworks. Every one of these processes produces light, particles, and noise. Dark matter, by contrast, whispers faintly amid the chaos. Even if it leaves a trace, that trace must be distinguished from countless natural fireworks already blazing across the sky. It's like trying to identify a single spark in the middle of a galaxy-wide bonfire. The signal is there, maybe, but extracting it from the background is a monumental challenge. And yet, that's what makes the search so captivating. Every strange anomaly, every unexplained glow, every excess in the data sends scientists back to their calculations. They model, debate, refine, and test. They chase the line between what's known and what might be hiding in plain sight. The process is patient, sometimes exasperating, but deeply human, a testament to our refusal to accept mystery as final. Each possibility, no matter how faint, is another step closer to understanding how the universe holds itself together. Each maybe is another thread in the tapestry of discovery. Occasionally, the results edge close enough to provoke genuine excitement. A signal emerges, the data align, the models fit, and for a moment it feels like the veil might lift. Then another explanation appears, more mundane perhaps, but equally valid. Maybe the gamma rays come from unseen pulsars. Maybe the positrons are produced by ordinary cosmic rays hitting interstellar dust. The strength of skepticism. In science, skepticism is the strongest tool we have. It's not negativity, it's rigor. Every maybe must survive 100 what-ifs before it earns a yes. Every candidate's signal must be tested, retested, and tested again from every angle. Alternative explanations must be considered and ruled out. Only then, when all other possibilities have been exhausted, can we begin to claim discovery. Still, the search continues with undiminished enthusiasm. New observatories like the Cherenkov Telescope Array, a next-generation ground-based gamma-ray observatory that will be far more sensitive than anything before it, and upcoming gamma-ray space missions promise unprecedented sensitivity. They'll map the sky in greater detail than ever, searching for the faint, diffuse glow of dark matter annihilation that might stretch across galaxies like cosmic phosphorescence. If such a glow exists, shimmering just below the threshold of current detection, we may soon see its outline flicker through the noise. We may finally distinguish the whisper of dark matter from the shout of conventional astrophysics. Poetry in the search. There's something poetic about this stage of the search. We are quite literally looking for shadows made of light, subtle signatures that only appear when something invisible briefly transforms into the visible. It's a dance of opposites where darkness might finally betray itself by the light it releases. Matter and antimatter meeting in mutual annihilation, the invisible becoming visible for the briefest instant before vanishing again. It's also a reminder that even negative results matter profoundly. Each non-detection sharpens our understanding, constrains the theories, and directs the next generation of searches. The absence of evidence in this case is not the evidence of absence. It's the boundary line of progress, the faint horizon we keep pushing forward, one measurement at a time. If we can't yet hear the whispers of dark matter underground, and the sky offers only ambiguous murmurs, then perhaps there's one more arena to explore, a place where the smallest building blocks of reality collide at energies not seen since the universe was newborn, revealing their hidden kin. Because if the universe won't show us its secrets naturally, we might just have to make them ourselves. Creating dark matter, the collider approach. When looking for something that refuses to shine, reflect, or collide with anything we can detect, astronomers turn their eyes to the sky in hope. But physicists have another approach entirely, one that's more direct, more audacious, and in some ways more human. If the universe won't hand over its secrets willingly, they'll try to recreate them in the laboratory. Instead of waiting patiently for dark matter to bump into us, they'll make the conditions where it might be born. This is the idea behind using particle colliders to hunt the invisible, smashing known particles together at incredible energies and seeing if anything goes missing in the aftermath. It's a little like shaking a box of puzzle pieces to see what falls out, or striking two rocks together to see what sparks emerge. The Large Hadron Collider, humanity's most ambitious experiment. The Large Hadron Collider, or LHC, near Geneva, is humanity's most ambitious version of that approach. Buried deep beneath the French-Swiss border, straddling the boundary between nations like the knowledge it seeks, straddles the boundary between the known and unknown. It's a 27-kilometer ring where protons are accelerated to 99.999999991%, the speed of light, and then steered into one another head-on. The collisions recreate the temperatures and densities that existed just moments after the Big Bang, a time when the universe was so hot and dense that matter as we know it couldn't exist. Only the most fundamental particles and forces were present. Out of those brief, violent encounters, entirely new particles can appear, particles that haven't been seen since the universe was less than a microsecond old. When the collisions happen at one of the four main interaction points around the ring, detectors surrounding the impact points record a storm of debris, showers of particles spraying out in every direction, each tracked and measured with extraordinary precision. Most of what emerges is well understood. Electrons, photons, muons, quarks recombining into protons and neutrons, and other members of the familiar particle family. But sometimes, amid that chaos, there's a hint of something strange, something that doesn't quite fit the expected pattern. The energy going in doesn't perfectly match the energy coming out. The momentum doesn't balance. Something appears to have taken a little bit of energy and slipped away unnoticed, like a thief in the night. Missing energy, the key clue. This is what physicists call missing energy, and it's one of the key clues they're watching for. If a new kind of particle were produced in the collision, one that doesn't interact with the detectors because it doesn't interact electromagnetically. It would carry energy off silently, leaving behind a measurable imbalance. In other words, if you smash protons together and part of the energy vanishes without explanation, it might have gone into creating a particle that refuses to talk to light, a perfect dark matter candidate. The concept is elegant and surprisingly intuitive once you grasp it. Energy, like money in a ledger, always has to balance. It's a fundamental law of physics. Energy cannot be created or destroyed, only transformed. Physicists know how much energy they put into each collision. They can account for almost everything that comes out, tracking particles, measuring energies, reconstructing the event. If the numbers don't add up, if energy is unaccounted for, something must be missing, and that missing piece could belong to the invisible universe. To find these absences, detectors such as ATLAS and CMS at the LHC, each one as large as a 5-story building, weighing thousands of tons and containing millions of sensors, record billions of collisions per second. Then sophisticated algorithms and armies of physicists sift through the data for signs of missing energy patterns. It's not about seeing the dark matter directly, it's about seeing its shadow, the shape it leaves in the sum of everything else. Complementing other approaches, this search complements what astronomers are doing in space and underground, while astrophysical observations show us where dark matter is and how it behaves on cosmic scales. Collider experiments try to show us what it might be at the most fundamental level. It's like investigating a mystery from two sides. One group follows the footprints across a landscape. The other tries to make the suspect appear in a lineup. The idea of creating dark matter may sound ambitious, even arrogant, recreating particles that have existed since the dawn of time. But it's actually quite natural when you think about it. In the early universe, when temperatures were unimaginably high, particles of all kinds were constantly colliding and transforming into one another. Dark matter wasn't special. It was just another participant in the cosmic soup. If dark matter was born back then, the right combination of energy and conditions should, in theory, recreate it. Of course, the trick is knowing exactly which recipe to use. Nature doesn't come with an instruction manual. Physicists can't just order one batch of dark matter, please, and wait for it to appear. They have to test every possible outcome, every subtle deviation from what's expected, and see if something new emerges from the noise. The challenge of noise. And noise, there is lots of it. The subatomic world is busy, chaotic, and wonderfully uncooperative. Random quantum fluctuations, background radiation, detector imperfections. Most anomalies turn out to be statistical flukes, like seeing faces in clouds or hearing voices in white noise. It takes extraordinary care to distinguish a real signal from the countless false alarms. Physicists have a running joke: when you can't find your keys, make new keys and see what goes missing. In their case, the keys are new particles hypothesized to unlock the door to dark matter. Every time they test a theory, supersymmetric particles, hidden photons, axions, or something even stranger, they're essentially making new keys and seeing which one fits the lock. So far, none of those keys have turned smoothly. The collisions at the LHC have been spectacular, confirming some of the great predictions of modern physics, including the discovery of the Higgs boson in 2012. But the Higgs wasn't the end of the story. It was just the beginning of another mystery, another chapter in the book. The Higgs connection. If dark matter interacts weakly with normal matter, it might also interact weakly with the Higgs field, the invisible field that gives other particles their mass. Perhaps there's a faint handshake between the visible and invisible universes through this field, a subtle coupling that we haven't yet detected. Physicists have been probing that possibility, looking for slight deviations in how the Higgs behaves, tiny cracks that might reveal a hidden world behind the curtain. Despite the lack of direct evidence so far, These experiments are far from failures. Every run of the collider rules out certain masses, energies and interaction strengths, narrowing the landscape where dark matter might hide. It's like searching a vast forest at night with a flashlight. Every area you illuminate doesn't just show you what's there, it shows you where not to look next time, focusing your search. And sometimes the journey itself yields treasures we didn't expect. Along the way, collider experiments have uncovered new insights into the building blocks of matter, the symmetries of the universe, the nature of the Higgs field, and even the behavior of the quantum vacuum itself. The pursuit of dark matter has become a kind of scientific compass, pointing toward new frontiers, even when the direct trail goes cold. Philosophical beauty in the search. There's also a philosophical beauty in the idea of using collisions, moments of intense energy and chaos, to uncover something so serene and enduring as dark matter. These machines, these cathedral-like structures of superconducting magnets and silicon detectors, are designed to create tiny explosions thousands of times per second. In these fleeting bursts of violence, scientists search for the stillness that defines the cosmos. Each flash of energy in the collider is like a miniature universe, expanding, cooling, particles forming and decaying, and perhaps producing a handful of invisible particles that slip quietly into the dark, never to be seen again. To detect those absences requires faith in precision. The detectors at the LHC are layered like giant onions, each shell designed to catch different kinds of particles. Charged particles leave tracks in silicon sensors, photons deposit energy in electromagnetic calorimeters, hadrons penetrate deeper into hadronic calorimeters, muons pass through everything and are caught by dedicated muon chambers in the outermost layers. When a dark matter particle is created, it passes through all these layers without leaving a trace. It's a ghost in the machine. The detectors measure everything else so meticulously, with such extraordinary precision that the missing energy stands out like a missing note in a symphony. The silence itself becomes the evidence. Looking to the future, even if the LHE doesn't find the smoking gun, the definitive proof of dark matter creation, it's laying the groundwork for the next generation of colliders, machines that will reach even higher energies, probing deeper into the unknown. There's always the possibility that dark matter lies just beyond our current reach, waiting for us to turn up the dial a little higher, to push the energies just a bit further. Plans are already being discussed for future circular colliders, linear colliders, and machines that could dwarf even the LHC in scale and ambition. The pursuit continues, not out of frustration, but fascination. Science thrives on questions that resist easy answers, and dark matter remains one of the most tantalizing of them all. Whether the key is hidden in the stars, buried deep underground, or created for a fraction of a second inside a particle accelerator, every approach brings us closer to understanding how the visible and invisible universes fit together. Each method offers a different window, a different perspective on the same underlying reality. And while we haven't found the missing piece yet, the act of looking has already changed how we see the cosmos. It's a reminder that discovery isn't just about finding new things, it's about realizing how much we still have left to learn, how vast the unknown remains. Somewhere in the interplay between light and dark, energy and silence, collision and stillness, the truth is waiting. The next step is to look not only deeper but wider, to keep an open mind, to question our assumptions, and to remember that even the most elegant theories sometimes need rewriting. Because as the search unfolds, it becomes increasingly clear that there may be more than one path to the unseen, and perhaps more than one kind of darkness altogether. Perhaps the universe is more complex, more subtle than we imagined, and that complexity is not a barrier, it's an invitation. When gravity itself might be wrong, modified gravity theories. For all the evidence pointing toward dark matter, not everyone has been convinced that an invisible substance is the only answer, or even the right one. Some scientists have wondered if perhaps we're asking the wrong question entirely. Maybe there's nothing missing at all, no hidden particles, no exotic matter drifting through space. Maybe, just maybe, our understanding of gravity itself isn't quite right. Maybe the universe is playing by a slightly different set of rules than we thought, and we've been trying to fit those rules into a framework that was never quite complete. If gravity behaves differently on larger scales than it does in our solar system or here on Earth, then galaxies spinning too fast or clusters holding together too tightly might not require any hidden mass to explain them at all. Perhaps the universe is simply operating according to laws we haven't fully grasped yet. The calculations we use work beautifully for launching satellites and predicting planetary orbits. But what if they need adjustment when applied to the vast emptiness between galaxies? The birth of Mund. This alternative view was first explored seriously in the early 1980s by physicist Mordechai Milgrom, who proposed something called modified Newtonian dynamics, or MOND for short. At the time, Vera Rubin's observations of flat galaxy rotation curves had just made headlines, shaking the foundations of astronomy. The outer stars of galaxies were moving faster than expected, much faster, suggesting either extra mass we couldn't see or a fundamental flaw in our mathematical understanding of motion and gravity. Milgrom wondered if maybe Newton's laws, while perfectly accurate in the laboratory or within our solar system where accelerations are relatively strong, needed a gentle tweak at extremely low accelerations, the kind you find at the distant edges of galaxies, where gravity's pull becomes whisper-thin, in regions where gravitational acceleration drops below a certain threshold. Perhaps gravity doesn't weaken exactly as Newton predicted. Instead, it might taper off more slowly, providing an extra boost that helps explain why stars in the outer reaches of galaxies don't drift away into the void. With this adjustment, subtle but significant, you could reproduce many of the same rotation curves that led astronomers to infer dark matter without adding any invisible material at all. No exotic particles, no hidden halos, just a single modification to the equation, governing how gravity behaves in extreme conditions. It was an audacious idea, and in some ways, beautifully simple. Where MOND succeeds, MUND works remarkably well for certain things. Almost eerily so, it can predict how stars move within many galaxies with impressive accuracy, sometimes better than dark matter models that require complex simulations and fine-tuning. It also explains some fine details that even dark matter simulations sometimes struggle with, such as the tight relationship between a galaxy's visible mass and its rotation speed, a pattern known as the Tully-Fisher relation. This relationship is striking. Observe any spiral galaxy, measure how much light it emits, which tells you roughly how much normal matter it contains, and you can predict how fast it rotates. The correlation is tight, universal, and surprisingly clean. It's as if galaxies obey a universal rule, and MUND seems to capture it naturally without requiring invisible matter to balance the books. For galaxies in isolation, MOND often performs beautifully. It's elegant, economical, and philosophically appealing. Why invent an entirely new form of matter when tweaking an old equation might suffice? To some researchers, this simplicity is not just convenient, it's a guiding principle. Science, after all, often favors the simplest explanation that fits the data. Where MUND struggles, but simplicity can be deceiving, and the universe is rarely content to let one neat equation solve everything. When astronomers tested MUND on larger scales, galaxy clusters for instance, the cracks began to show. The extra gravitational pull required to hold those massive clusters together was far greater than MUND could provide on its own. Even with the modified equations, the visible matter plus the MUND effect wasn't enough. To make the math work, even MUND had to invoke some unseen matter, perhaps neutrinos with mass, or some other form of missing material. A touch of irony that wasn't lost on its critics. If Mund still needed invisible stuff to explain clusters, had it really solved the problem or just moved it somewhere else? The theory also ran into serious trouble when confronted with the cosmic microwave background. The ancient light from the early universe now stretched into faint microwaves by billions of years of expansion. The delicate pattern of temperature ripples in that background encodes the balance of matter, energy, and gravity in the newborn cosmos. Those patterns match beautifully with the predictions of the dark matter model, fitting together like pieces of a cosmic jigsaw puzzle. But they are far harder to reproduce with modified gravity alone. Mund struggles to explain why the universe looks the way it does on the largest scales, why structure formed when and how it did, and why the tiny fluctuations in the early universe evolved into the galaxies and clusters we see today. It's as though Mund could draw a convincing map of a city's streets, accurate, detailed, and useful, but struggle to capture the mountains, rivers, and coastlines surrounding it. The broader family, modified gravity theories. Still, Mund sparked a new and valuable way of thinking about gravity. If Newton's laws might need adjusting, perhaps Einstein's general relativity, our more complete and sophisticated description of gravity, might need refinement too. After all, general relativity was developed and tested primarily in the context of the solar system, where gravity is relatively strong. What if, on truly cosmic scales, spanning millions or billions of light years, subtle corrections become necessary? This led to a broader family of theories called modified gravity, or Thieves' tensor vector scalar gravity being one prominent example. These ideas introduce additional fields or forces that subtly change how gravity behaves over vast distances or in extremely weak gravitational environments. Some versions even try to explain both dark matter and dark energy, the mysterious force driving the universe's accelerating expansion, as different aspects of a single deeper principle. These modified gravity models can sometimes mimic the effects of dark matter surprisingly well. They offer elegant explanations for galaxy rotation curves, and they avoid the need to invent an entirely new form of matter that has never been detected in any laboratory. For many physicists, that simplicity carries weight. Why add a whole new kind of particle with unknown properties and interactions, if a tweak to the fundamental equations of gravity could do the same job? The evidence favors dark matter, but the more scientists rigorously test these theories across multiple scales and contexts, the more the cumulative evidence seems to favor dark matter. When researchers simulate the large-scale structure of the universe, the cosmic web of filaments, walls, and voids that stretches across billions of light years, dark matter naturally produces the observed patterns. The simulations match reality with stunning accuracy. Modified gravity theories, on the other hand, tend to struggle with those same details. They can explain individual galaxies perhaps, fitting their rotation curves elegantly, but galaxy clusters, the gravitational lensing patterns, the subtle fingerprints left in the early universe's light, those remain challenging. It's a little like trying to navigate a landscape using two different maps. One map, the dark matter model, includes every hill, river, valley, and bridge. The other, modified gravity, shows most of the roads accurately, but some critical connections are missing or unclear. You can get around using either map, and for certain journeys one might even work better, but only one map seems to match the terrain faithfully in all directions across all scales. And that comprehensiveness matters deeply in science, where theories must not only explain individual phenomena, but fit together into a coherent whole. Respect for alternative ideas. Even so, Mund and its successors have earned lasting respect in the scientific community, and deservedly so. They serve as an important reminder that no idea, however successful or widely accepted, should go unchallenged. The history of science is full of moments when the universe surprised us, when what seemed certain in one century became incomplete or incorrect the next. Newton's gravity worked beautifully for centuries until Einstein showed it was an approximation of something deeper. Might Einstein's equations also be approximations? Modified gravity keeps that humility alive, that openness to being wrong. It's a kind of philosophical counterweight to dark matter, a quiet voice in the room saying, what if we've simply misunderstood how gravity works? Some researchers are even exploring hybrid approaches, attempting to combine aspects of both views. Perhaps gravity is slightly modified on cosmic scales, and there's also a form of unseen matter. The universe may not be an either-or system, but a both-and, as so often happens when humans try to simplify something profoundly cosmic into a single tidy rule. For now, though, the balance of evidence strongly supports dark matter. Its fingerprints are everywhere, in the bending of light around galaxy clusters, in the formation of cosmic structure, in the motions of stars and gas within galaxies, and in the ancient echoes of the Big Bang preserved in the cosmic microwave background. No single modified gravity theory has yet been able to reproduce all of those clues simultaneously, across all scales and contexts. That doesn't mean the challengers have failed, only that the mystery remains richer and more nuanced than we initially expected. Every good alternative hypothesis forces the standard model to sharpen itself, to test its assumptions more rigorously, and to clarify what we truly know versus what we've merely assumed. In that way, even theories that don't ultimately prevail still advance the story. A dialogue that keeps science alive. The conversation between these ideas, between unseen matter and unseen rules, is what keeps cosmology vibrant and alive. One side imagines a universe filled with invisible substance, particles that interact only through gravity. The other imagines a universe whose fundamental laws subtly evolve depending on scale or environment. Both are sincere, rigorous attempts to make sense of the same set of clues, and both remind us that our understanding of gravity, though powerful and precise, may not yet be complete. Perhaps in the end, the truth will borrow a little from each perspective. A universe that bends its laws gently in extreme conditions while still hiding something substantial beneath the surface. Or perhaps the answer will be something else entirely, something we haven't yet imagined, a third path that reframes the question altogether. Whatever the final answer turns out to be, the search itself has deepened our grasp of the cosmos in profound ways. Every equation written, every simulation run, every late-night debate in a quiet observatory, or over coffee at a conference adds another thread to the tapestry of discovery. The process of questioning, testing, and refining is as valuable as any single answer. For now, dark matter remains the leading explanation, supported by the weight of evidence gathered from across the sky, from deep underground laboratories, and from particle colliders. But it's worth remembering that science advances not only through answers that settle debates, but through questions that refuse to settle, questions that keep us looking, thinking, and wondering. And in the grand search for the invisible, every alternative path explored, even the ones that wind back on themselves or lead to dead ends, helps illuminate the way forward. They teach us where not to look, what doesn't work, and sometimes, just sometimes, they reveal hidden connections we hadn't noticed before. With the debate still alive and curiosity undimmed, it's time now to step back from individual theories and technical arguments and take in the bigger picture, to look at what the universe is truly made of and how all its strange and disparate ingredients fit together into a single, astonishing whole. The cosmic inventory. What is the universe made of? When you step back and look at the universe as a whole, taking in the grand cosmic census, something quietly astonishing comes into focus, something that shifts your entire perspective on existence. Everything you can see with your eyes, with telescopes, with any instrument that detects light, every star burning in the night, every planet orbiting quietly, every nebula glowing softly, every atom that has ever existed in any form, all of it together makes up only a tiny fraction of what's actually out there. The glowing galaxies scattered across the sky like jewels on velvet, the clouds of gas drifting between them, the dust lanes tracing spiral arms, the molecules in your body, the air you breathe together, they amount to just about 5% of the cosmic total. 5%, that's it. Everything tangible, everything luminous, everything we've ever touched or seen or measured directly. The rest, the vast unseen majority, belongs to realms we cannot touch, cannot see, cannot interact with, except through their gravitational influence. Roughly 27% is dark matter, that invisible scaffolding we've been tracing throughout this journey, and an even more mysterious 68% is dark energy, a force or property of space itself that we'll touch on gently in a moment. A universe made mostly of nothing. It means that most of the universe is invisible, not because it's hiding behind something, or because our instruments aren't good enough, but because it exists in forms that are fundamentally different from the matter we know. The universe, in the simplest and strangest terms, is made mostly of nothing, and yet that nothing is precisely what gives it structure, motion, and the capacity for life. Imagine standing inside a vast cathedral, so enormous that its walls vanish into darkness, and you can barely perceive its boundaries. The beams of light streaming through stained glass windows, illuminating the floor in brilliant colours, that's the stars and galaxies, the luminous 5%. Beautiful, captivating, impossible to ignore. But the pillars holding up the ceiling, the arches shaping the space, the flying buttresses supporting the walls, and even the air that fills the vast interior, that's the dark matter and dark energy. They don't glow, they don't draw the eye. But without them, the cathedral would collapse into rubble. The universe's beauty comes not only from its light, but from the dark scaffolding that allows the light to exist in the first place. Dark matter, the cosmic glue. Dark matter, that quiet cosmic glue we followed through galaxies and clusters, makes up about a quarter of everything that exists. It binds galaxies into clusters and holds stars in their orbits. It gives the universe its large-scale shape, drawing the grand filaments that stretch between galactic cities like threads in an infinite web. Without it, the cosmos would be thin, diffuse, and featureless, like fog without form, light without structure. Every galaxy, including our own Milky Way, sits nestled inside a massive halo of dark matter several times larger and more massive than the visible galaxy itself. These halos are the true bodies of galaxies. The visible stars and gas are just the bright centers, like glowing hearts within invisible giants. Dark energy. The cosmic breath. And then, beyond dark matter, there's dark energy, the most mysterious component of all, filling the remaining 2/3 of the universe. It's not matter at all, but rather a property of space itself, or perhaps a field pervading everything. It gently pushes everything apart, causing the expansion of the universe to accelerate over time. It's as though space is slowly exhaling, stretching the galaxies farther from one another with every passing billion years. Where dark matter pulls things together through gravity, dark energy pushes them apart. The two forces are locked in a cosmic tug-of-war, and currently, dark energy is winning. The universe is expanding faster now than it was billions of years ago, and that acceleration shows no sign of slowing. Dark energy is even more mysterious than dark matter. We don't know what it is, where it comes from, or why it has the strength it does. Some theories suggest it's the energy of empty space itself, quantum fluctuations in the vacuum. Others propose it's a new kind of field, dubbed quintessence, that changes over time. Still others wonder if it's a sign that our understanding of gravity needs modification on the very largest scales. A story of balance. These numbers, 5% ordinary matter, 27% dark matter, 68% dark energy might feel abstract like statistics in a textbook, but together they tell a profound story of balance and interdependence. The universe isn't a vast emptiness randomly sprinkled with light. It's a carefully structured fabric, a composition where the unseen dominates the melody, but allows the seen to sing. Even though dark matter and dark energy remain unknown in their fundamental nature, their effects are written everywhere we look. The way galaxies spin, maintaining speeds that should tear them apart. The way massive clusters bend light, creating cosmic magnifying glasses. The way the cosmic microwave background ripples with precise patterns. The way the universe's expansion accelerates rather than slows. All of it speaks in the language of the invisible. And yet, this dominance of darkness doesn't make the universe bleak or cold. Quite the opposite. It gives the cosmos a strange kind of elegance, a reminder that what's most essential to existence isn't always what we can see or touch. The atoms that make up everything familiar, stars, oceans, mountains, trees, people, are like rare jewels set in an ocean of the unseen. We are, in a profound sense, beings made of rare material, sculpted from the leftovers of cosmic creation, carried along by forces we cannot see. Comfort in the unknown. There's comfort in that realization too. The universe is enormous, yes, incomprehensibly vast, but it isn't cold or indifferent. Its seeming emptiness is full of quiet purpose and hidden activity. The spaces between galaxies aren't true voids. They are regions where gravity and energy perform a delicate dance, a cosmic conversation that has continued uninterrupted for nearly 14 billion years. Even the word nothing feels inadequate here, almost misleading. Space itself is not empty in any meaningful sense. It hums with energy, with fields, with quantum fluctuations. Particles blink into existence and vanish again in less than an instant. Gravity stretches and curves space. Light travels through it, and dark energy fills it with gentle, persistent pressure. What we casually call nothing is in truth the most fundamental something there is. The cosmic pie chart. Astronomers sometimes describe this breakdown as a cosmic inventory or a pie chart of existence. If you were to make such a chart, only a slim slice, barely visible, would represent everything known and luminous. The rest of the chart would be labeled with question marks, or with terms like dark matter and dark energy, that are really just placeholders for we don't know yet. And yet, those question marks are precisely the reason the pie exists at all. They're not flaws in the recipe. They're essential ingredients. It's a reminder that ignorance in science isn't a void to fear or a failure to lament, but an invitation to explore, to wonder, to keep asking questions. The fact that we can measure the proportions of the universe so precisely, calculating to within a few percentage points what fraction is matter, what fraction is dark matter, what fraction is dark energy, even without knowing what most of it actually is, represents one of the quiet triumphs of human curiosity and ingenuity. We've learned to weigh the invisible, to map the unseen, to measure forces we cannot touch. We are rare, and that's beautiful. The story of dark matter and dark energy shows us that the unknown isn't an obstacle to knowledge, it's the wellspring of it. Every mystery uncovered by science doesn't diminish the world, it deepens it. The more we learn about what the universe hides, the more astonishing it becomes that anything shines at all. Our understanding is still evolving, still incomplete. Future telescopes may reveal the true nature of dark matter particles. New theories may finally explain what dark energy really is, or show us that it's something even stranger than we imagined. Experiments underground may finally catch that elusive whisper of a dark matter collision, or perhaps the answer will come from a direction we haven't thought to look yet. But for now, in this moment, we live in an age of wonder, knowing that our entire existence, every thought, Every experience, every breath plays out in a universe where almost everything is invisible, and yet everything works together in perfect, inexplicable harmony. Looking up with new eyes. When you look up at the night sky now, after this journey, remember that you're not just seeing stars, you're seeing the surface of a vast and invisible ocean, the faint shimmer atop depths we can't yet reach. The galaxies are lanterns drifting in that ocean, held aloft by the unseen tides of dark matter and carried slowly outward by the gentle breath of dark energy. It's tempting to think of ourselves as small in such a universe, insignificant specks in an incomprehensible vastness, but perhaps it's better to see it the other way around. We are rare concentrations of visible ordinary matter, brief and luminous, complex and aware, able to ask questions about the darkness that sustains us. We are the eyes through which the universe observes its own invisible body. And maybe that's the most extraordinary thing of all, that something made mostly of nothing can give rise to consciousness, to curiosity, to wonder, to awe, that the same gravitational forces shaping galaxies have, through an intricate and improbable chain of events stretching across billions of years, shaped minds capable of wondering why. Minds that can look up, trace the invisible with mathematics and imagination, and feel a strange kinship with the darkness. So yes, the universe is mostly dark, mostly invisible, mostly beyond our direct reach. But within that darkness lies the architecture of everything we know and love. The quiet pillars of the cosmic cathedral, the loom upon which the tapestry of existence is woven. The darkness is not an absence but a foundation, not an end but a beginning. As we drift toward tomorrow, the stars overhead remind us that light is precious, precisely because it is rare, and that the spaces between stars are not empty but full of meaning. The universe, made mostly of nothing, is somehow the greatest something there has ever been, vast, silent, and softly glowing with the promise of what we have yet to understand. The future of darkness, an eternal vigil. The night sky we see today is only a temporary arrangement, a fleeting snapshot in a much longer story that stretches far beyond human comprehension. Galaxies glitter like scattered diamonds, stars burn with fierce nuclear fires, clusters hold together in gravitational embrace, but nothing in the cosmos lasts forever, no matter how eternal it might seem from our brief human perspective. Even the brilliance of starlight is just a momentary flare in a universe that stretches across not millions or billions, but trillions upon trillions of years, in the far future, so distant that our sun will have long since died, our galaxy will have merged with Andromeda, and the very concept of now will have lost all meaning. It will be the dark matter that remains, silent, invisible, and steadfast, preserving the faint ghost-like outlines of structure, long after every last photon of light has flickered out. Dark matter is the quiet sculptor of cosmic architecture, and that architecture will endure long after its luminous tenants have gone to sleep. Stars will die, their nuclear furnaces finally exhausted. Galaxies will dim, their spiral arms fading like old photographs. And yet the dark scaffolding that holds them in place will persist, unchanging, patient as it has always been. The long goodbye of the stars. The halos that once cradled galaxies in invisible embrace will continue to exist, slowly diffusing and spreading out, like ancient ruins standing long after the civilization that built them has crumbled to dust. Over unimaginable timescales, periods so vast that a billion years becomes the blink of an eye, the expansion of the universe will continue to stretch space itself. Dark energy, that gentle but relentless pressure woven into the very fabric of the cosmos, ensures that galaxies will drift farther and farther apart. Clusters that are gravitationally bound together will remain cohesive for an incredibly long time, held together by their own gravity and dark matter halos. But beyond those clusters, the rest of the universe will recede into obscurity, pulled away by the accelerating expansion. The night will deepen, not through sudden collapse or catastrophe, not through any dramatic cosmic event, but through distance, a gradual, gentle pulling apart of everything that was once connected. In that distant future, the stars will continue their slow, inevitable evolution. The bright blue giants, those massive, brilliant stars that shine so fiercely, will burn out first, their light extinguished in what seems like a cosmic instant compared to eternity. They live fast and die young, consuming their fuel in mere millions of years. Smaller, redder stars, the dim dwarfs that barely glow in our current sky, will burn quietly for trillions of years. Their long, steady lives will outlast everything we see today, every civilization that might ever arise, every thought that might ever be thought. They are the universe's longest vigil keepers. But even they will eventually fade, cooling slowly into black dwarfs, cold, dark cinders that emit no light at all, so dim that the night will once again become the universe's dominant color. Ghost towns in the void. The galaxies themselves, once radiant cities of billions of stars, will become ghost towns drifting through an ever-expanding void. Their dark matter halos will remain as vast invisible envelopes, still shaping the paths of any remaining stellar remnants, still tracing the outlines of the invisible cosmic web that once tied the universe together in an intricate tapestry. But with no light left to reveal them, they will exist as shadows without contrast, structure without substance, form without visibility. By this time, we're talking perhaps 100 trillion years from now, or more. The distances between galaxy clusters will have grown so vast that light from one will never be able to reach another, no matter how long it travels. The expanding space between them will stretch faster than light can cross it. Each cluster will become an island of night, surrounded by an ocean of absolute nothingness. To any observer that might exist in such an era, though it's hard to imagine consciousness surviving in such conditions, the universe would appear strangely empty, almost incomprehensibly so. The cosmic expansion would have carried away the rest of the cosmos beyond the horizon of visibility. Every observer would be alone in a bubble of space, floating on a silent sea with no other shores in sight. The memory of structure. And yet, even in that profound stillness, the memory of structure will endure. The gravity of dark matter, though invisible and unfelt, will continue to define the shape of things long after everything luminous has faded into darkness. The invisible halos, the ancient filaments now stretched impossibly thin, the silent skeleton of the universe, all will remain as the final architecture of existence, the last testament to how things once were. In time, even more time, time beyond imagining, even black holes, those great engines of gravity that seem so permanent, will begin to evaporate through a process called Hawking radiation. Stephen Hawking showed that black holes aren't truly black. They emit faint radiation and slowly lose mass. Over stupendously long spans of time, we're talking 10 circumflex, 100 years or more, they'll fade into nothing, releasing their captured energy into the vastness as faint whispers of light. What remains then? Only the dark matter particles themselves, drifting endlessly through an ever-expanding universe, too diffuse to ever meet again, too scattered to interact, and yet still quietly marking the places where galaxies once shone, where stars once burned, where perhaps life once looked up at the sky and wondered about its place in the cosmos. A serene vision. It's a vision of the future that feels strangely serene rather than sad. There is no explosion marking the end, no abrupt termination, no cosmic catastrophe, just a gentle unweaving of the fabric of brightness, a long, slow return to stillness. The universe doesn't die in any dramatic sense. It simply falls asleep like a person drifting off after a long and eventful day. The structures formed by dark matter, the galaxies, the clusters, the cosmic web will dissolve so gradually that even time itself might seem to slow in sympathy. If one could somehow stand in that far future, perhaps on some lonely remnant planet orbiting an ancient brown dwarf, the last ember of stellar activity, the sky would be dark and quiet beyond all comprehension. The faint glow of a dying galaxy might shimmer in the distance like a half-remembered memory, surrounded by emptiness so deep it would seem to stretch forever. The cosmic web, that great network of dark matter and galaxies that once spanned the observable universe like neural pathways in a vast cosmic brain, will by then be a faded echo, its strands stretched beyond reach, its connections lost to distance, its patterns dissolved by time and expansion. Beauty in the darkness. And yet, in that future darkness, there's a quiet, profound beauty. The same fundamental forces that shaped the early universe will still exist, unchanged and patient as ever. Gravity will still pull, gentle and persistent. Dark matter will still have mass, still curve space-time, still trace the outlines of ancient structures, and dark energy will still whisper its quiet expansion, still pushing space apart with the same gentle insistence it has shown for billions of years. The universe will continue to be, even if it no longer shines, it will exist in a state of dark equilibrium, a final resting configuration that is in some ways more honest than the brief luminous age we happen to inhabit. It's strange and humbling to think that the story of light, the story of stars, planets, galaxies, and perhaps life, is just one chapter in a much longer book written mostly in darkness. We happen to live in the bright Middle Pages, the brief, glorious moment when galaxies still gleam and night skies still sparkle with countless points of light. Billions of years from now, those lights will fade one by one, but the underlying structure, the quiet geometry traced by dark matter, will remain a permanent record of how everything once was. Not an end, but a continuation. From a cosmic perspective, the future is not something to fear or mourn. It's simply the natural continuation of a universe that has always balanced opposing forces, creation and dissolution, brightness and shadow, matter and void. The same physics that allowed galaxies to form in the first place will one day allow them to fade, and in that fading, there is a kind of peace, a slow return to equilibrium as the universe lets go of its luminous energy and settles into its dark, enduring form. We tend to think of darkness as emptiness, as the absence of something valuable, but in the cosmos, it's the opposite. The dark will inherit everything. It is the keeper of structure, the custodian of memory, the foundation upon which everything else is built. When the last photon is released and the final star goes cold, the universe will still be there, quiet, vast, and patient beyond all human imagining. And perhaps, just as the stars once rose from darkness in the early universe, something else might rise again in some form we cannot yet imagine. The universe has surprised us before with its creativity. Its silence in that distant future may be less an ending than a pause between movements, a rest in the cosmic symphony before the next theme begins. But for now we're lucky, incredibly, impossibly lucky, to live in the era of light when galaxies still glow, when the Milky Way still paints the sky with its luminous band, and when we can still look up and ask what will come after. The fate of the dark is not a tragedy, but a continuation, the long echo of creation itself. The islands of night will drift apart on their silent sea, each carrying within their dark matter halos the memory of the light that once was. And though the future will belong to the dark, the present, this shimmering temporary age of stars, belongs to us. The beauty of darkness, a foundation, not an absence. Darkness has always carried a certain reputation in human culture, something to be feared, banished, or filled with light. We speak of dark times as periods of suffering. We describe ignorance as darkness. We use light as a metaphor for knowledge, goodness, and clarity. Yet, when you look closely at the universe, when you really examine how reality is constructed, you find that darkness is not the enemy of light, but its foundation. Every star, every galaxy, every flicker of brilliance exists because the dark made room for it. The invisible is not what hides the cosmos or obscures our understanding. It's what holds everything together in the first place. The tapestry metaphor. If you imagine the universe as a great tapestry hanging in some cosmic gallery, the light, the stars and galaxies we see, is only the embroidery, delicate threads of gold and silver glinting across the surface, catching the eye, drawing our attention. But the true fabric beneath, the sturdy weave that gives the tapestry its shape and strength, the loom upon which everything is woven, that is dark matter. It stretches between galaxies, linking them in patterns we can trace mathematically, but never see directly. Through its silent, invisible strength, the cosmos found its form. Darkness, then, is not absence. It is structure. It is the silent architecture of reality. It is the stage upon which the brief, brilliant play of light unfolds. A partnership, not a battle. The story of the universe is not a battle between light and dark, not a cosmic struggle with winners and losers. It's a partnership, a collaboration, a dance. From the first moments after the Big Bang, darkness shaped the stage so that light could perform its brief and brilliant act. The stars we see twinkling in the night sky are like glowing notes in a symphony composed mostly in quiet keys. Without the unseen matter surrounding them, gravitationally binding them, creating the conditions for their formation, their music would never have begun. It's profoundly humbling to realize that the universe does not depend on visibility for its beauty or its meaning. The galaxies gleaming in deep space photographs are breathtaking. Yes, but they're breathtaking, not because they're rare exceptions to darkness, but because they reveal what the darkness can do when given time and gravity. Every swirl of starlight, every arm of a spiral galaxy, every cluster of ancient stars, all of it exists because dark matter created the gravitational wells within which normal matter could collect, compress, and ignite. We are children of both. We ourselves are children of both the light and the dark. The atoms in our bodies were forged in the hearts of stars. That's the luminous heritage we often celebrate. But those stars only existed because dark matter created the gravitational scaffolding for galaxies to form. The Earth beneath our feet orbits a star that exists in a galaxy held together by dark matter. The food we eat grows under a sun held in its galactic orbit by invisible forces. Every breath we take, every thought we think, occurs within a universe whose very structure depends on what we cannot see. There's something deeply beautiful about that interdependence. It reminds us that reality is richer and stranger than what appears on the surface. It teaches us that the most essential things are often invisible, not just in physics, but perhaps in life itself. Love, consciousness, meaning, purpose, none of these things can be seen directly, and yet they shape our experience as profoundly as dark matter shapes the universe. The lesson of dark matter. Perhaps the greatest lesson of dark matter is one of humility and wonder. For centuries, humanity assumed that what we could see was most or all of what existed. We built our physics, our cosmology, our entire understanding of the universe based on the visible, and then, gradually, evidence accumulated that we were missing most of the story. The universe was far stranger, far richer, far more mysterious than we had imagined. That realization didn't diminish the cosmos. It deepened it immeasurably. Every mystery solved revealed new mysteries. Every question answered spawned a dozen more, and that is exactly how it should be. A universe fully understood would be a universe fully contained, limited, finished. But a universe still full of darkness, still hiding secrets, still whispering clues we haven't yet learned to interpret, that's a universe worth exploring. So when you look up at the night sky now, after this long journey through the invisible universe, see it with new eyes. Those stars are precious precisely because they are temporary, because they represent a brief moment when matter becomes visible and luminous. But the darkness between the stars is not empty. It's full of the invisible matter that made those stars possible. The darkness is not the end of the story. It's the beginning, it's the foundation, it's the keeper of structure and the custodian of possibility. It's the quiet strength that allows the light to shine. We live in a universe made mostly of nothing, and yet that nothing is the greatest something there has ever been, vast, silent, invisible, and yet supporting everything we know and love. The darkness holds the galaxies. The darkness shapes the cosmos. The darkness is not what we must overcome, it's what we must learn to appreciate, to respect, and perhaps eventually to understand. And until we do, we'll keep watching, keep listening, keep searching, in deep underground laboratories and mountaintop observatories, in particle accelerators and space telescopes. Humanity continues its patient vigil. We're learning to hear what the universe whispers, rather than what it shouts. We're learning to see with mathematics what remains invisible to light. We're learning that darkness is not the absence of knowledge, but an invitation to discover. The search for dark matter is ultimately a search for understanding. Understanding of what we are, where we came from, and what holds it all together. And even if we never find all the answers, the journey itself transforms us. It teaches us humility, patience, wonder, and awe. So rest now, knowing that you float in an ocean of invisible matter. Close your eyes and feel the darkness as a presence rather than an absence. The same dark matter that holds galaxies together in the void is here, around you, flowing through this room, though you cannot feel it. You are surrounded by mystery, supported by the invisible, cradled by forces you cannot see. And in that darkness, there is beauty, there is structure, there is meaning. The universe, in all its vast and invisible majesty, continues its slow dance through time, and we are lucky enough to witness this brief luminous moment in its endless story. Sleep well, knowing that darkness is not something to fear, but something that makes the light possible, and dream of invisible oceans, silent forces, and the quiet architecture of everything that is.